Now, in this particular chapter, like you can see, there is some introduction. Let's understand what it says. Electricity, magnetism were separate for a long time. They were considered to be unrelated. In the early decades, experiments by Oersted, Ampere, etc., they showed that electricity and magnetism are interrelated. They found that moving charges produces magnetic field. An electric current deflects magnetic compass needle placed in its vicinity. The natural question arises like this: is the converse also true? Like, can magnetism create electricity? Okay, the answer to that was basically found by Michael Faraday's experiments in England and Joseph Henry in USA, which were in 1830. And they found out that electric currents were created in coils which were allowed changing magnetic fields inside of them. And we are going to study this particular phenomena where changing magnetic fields creates electric currents. This electricity which is generated is called as electromagnetic induction, this phenomena. And when Faraday made public his discovery that relative motion between the magnet and the loop produced currents in the coil, he was asked, what is the use of it? His reply was, what is the use of a newborn baby? And the phenomena of electromagnetic induction is not merely theoretical or academic interest, but of lot of practical use. Imagine a world where there is no electricity, no electrical lights, no trains, no phones, no personal computers. The pioneering experiments of Faraday and Henry have led directly to the development of all the modern day generators and transformers, and the whole civilization owes this progress to the great extent of the discovery of electromagnetic induction. Okay, I'll tell you. First of all, remember, people thought that electricity and magnetism were separate and unrelated. Like we have electric force, charges, they repel or attract. Magnets, they attract or repel. So one branch was electricity, one branch was magnetism. Even when you were a kid, you thought electricity is a separate topic, magnetism is a separate topic. Later on, it was proved that experimentally that the experiments on current, electricity by Oersted, etc., established the fact that electricity and magnetism are actually interrelated to each other. They are actually interrelated to each other. They are not separate. They are not separate. It was considered separate, but actually they are not separate. Like whenever you pass current through a wire, it produces magnetic field. It can affect magnetic coils or magnetic needles. Isn't that right? So we know even a charge which is thrown in a magnetic field, it gets affected by it and it will get deflected by a force F is equal to QV cross B. If you notice, Q is the branch of electricity, B is the branch of magnetic field. Both the things coming together was establishing the fact that electricity and magnetism are related to each other. It is like Pandu and Champa, when they got married, they were casually talking about their childhood. And you know what, in my childhood, when I was 14 years old, I had gone to see this nice place in Goa. Champa was like, yeah, you know what, even I went to Goa when I was 14 years old. Then they were seeing through their pictures, Instagram, and then they realized, oh my God, we were at the same place at the same time. Oh, and you know what, I was there at that same restaurant, that same food festival was there. Oh, even I was there. Oh, wait a minute, you are there in my background picture. Hey, wait a minute, Pandu, I can see you in my background. So they found out they are related. So same thing happened with electricity and magnetism. Now, since electricity can produce magnetic field, current carrying coil can produce magnetism, current carrying wires can affect magnetic needles. The reverse, can magnetism create electricity? Can magnetic fields create electric field? Reverse. The answer is yes. So basically, if electric currents can deflect magnetic needle, the natural question is the converse possible. Can moving magnets produce electric currents? Such a relationship, is it possible? The answer to that is an astounding yes. It is possible. And that is what this chapter is all about. We will study this phenomena associated with magnetic fields in which electric current is created by changing the magnetic fields, and such an effect is called as electromagnetic induction. Now, Papa, this Faraday and Henry, they faced exact same lol movement, the complete, one palm face movement, same thing like what we or our kids, feel. Mom, Dad, you know what? I got first prize in drawing competition. Imagine your parents saying, so what? What will you do with first prize in drawing competition? What about mathematics? But I got first prize in mathematics. First prize in drawing competition. So, what about board marks? No interest only. Same thing Faraday Papa felt. Faraday, when he made his discovery that, hey, listen, I produced current inside a coil and I moved a magnet. People are like, so what? Like this they did. What is the use of this? His reply was, what is the use of a newborn baby? Got it? Understood? Yeah. So, this is exactly what he faced during that time. So, if you thought that your problems are just new, no, these problems have always been existing throughout our history, and a lot of people have faced this kind of criticism. So don't be bothered. Don't be bothered. I hope this is clear. Yes, Madhumati. Yes, Krishna. Hi, Janan. Jasmine. All right, Pratibha. Great. Hi, Suchi Mama. Nice to see all of you back over here. Great. So now that is what we are going to see, and all the modern day discoveries and things are basically we owe to Faraday and Henry. Yeah, that's what they say. Okay, fine. What are those experiments? The discovery and understanding of EMI, electromagnetic induction, are based on long series of experiments carried out by Faraday and Henry. We shall now describe some of these experiments. So, shows a coil connected to a galvanometer. When the north pole of a magnet is pushed towards the coil, the pointer in the galvanometer deflects, indicating the presence of electric field. The deflection lasts long as the bar magnet is in motion. Okay, what are the discoveries that he got? So, the galvanometer deflects, indicating the presence of electric current. The deflection lasts as long as the bar magnet is in motion. The galvanometer does not show any deflection when the magnet is held stationary. These are the observations, you should know it. The magnet is pulled away from the coil, galvanometer shows deflection in the opposite direction. Shows deflection in the opposite direction, which indicates reversal of the current's direction. Moreover, when the south pole of the magnet is moved towards or opposite, the deflection in the galvanometer are now opposite, and further the deflection is found to be larger when the magnet is pushed towards or pulled away from the coil faster. Instead, when the bar magnet is held fixed and the coil is moved, the magnet is held fixed and the coil is moved towards or away, the same effects are observed. It shows that finally the relative motion between the magnet and the coil is responsible for generation. This generation is called as induction of electric current in the coil. Second experiment, bar magnet is replaced by secondary coil and a steady current is produced in that particular coil, and the coil is moved towards etc. the coil, another coil. It shows another deflection. This indicates electric current is induced. When this coil is moved away, again it shows deflection, but in the opposite direction. So basically the conclusion is the same effects are observed again in the relative motion between the coils that induces the electric current. So here the bar magnet is replaced by a secondary coil connected to a battery. So let's understand what and all is mentioned over here. So for that, we will just go to PHET, yes, and we will just go to electricity, magnetism and circuits. Okay. Now, see guys, we know that whenever you have a coil which carries current, see this is a bar magnet. See, this is a bar magnet. You can see this bar magnet, it produces a magnetic field. You can see a compass gets deflected around it. It shows that, there is magnetic field around it. Whichever direction it points, it shows that direction the magnetic field is there. And you can see the magnetic field lines are like this. If I make the magnetic strength stronger, you can see more field lines. If I make it weaker, it will be less number of field activity. Here the strength is more, here the strength is less. Okay. Now the same phenomena will repeat if I, instead of a permanent magnet, if I use basically an electromagnet. This is an electromagnet, basically a current carrying coil. Can you see the field is again exactly the same as a bar magnet. So current carrying coil produces a magnetic field around it. The magnetic compass deflects exactly the same way. If I reverse the direction of the current, the magnetic field also reverses. White becomes red, red becomes white. You would notice any point, let's say this one. White will become red, red will become white. Right? Because the direction of the current has reversed, so the field will also reverse. Okay. Fine, sir. Great. This is what an electromagnet is, sir. Okay. So what is the Faraday's experiment, sir? Okay. So let's go to Faraday's experiment now. So as per Faraday's experiment, what he did was, yes, let's have pickup coil. Yes, over here. Okay. This is exactly a simpler version of Faraday's experiment. The actual version, the schematic, diagrammatic version in NCERT is shown over here. It's the same setup, guys. Just I have shown it in a slightly different way. That's all. It's the same thing. Okay. Observe now. What is there? There is a coil. Instead of a galvanometer, there is a bulb. What does a galvanometer do? It shows how much current is there. I can use a bulb also to see current is there, or I can use a galvanometer which shows the current. If it deflects this way, current is moving in one direction. If it deflects the other way, current is going in the other direction. No deflection means no current. More deflection means more current. Okay. What have I done? Taken a magnet. Right now the magnet is just kept over here. Is it showing any deflection? No. Which means, is there any electricity produced? Answer is no. I hope this is absolutely clear. Okay. So now what we are going to do is we are going to move the magnets. Now what we are going to do is basically we are going to move these particular magnets and see what happens. So if I move this magnet, oh, do you see? There is some deflection over here. And what do you see? The magnetic field in this region, is it not changing, guys? So this shows that whenever the field passing through a coil changes, that produces electricity. A static magnetic field does not produce electricity. Changing field, right now the fields are stationary, it is not changing. But the moment I move the magnet, you can see the fields are basically changing. So that is what produces electricity. So this was the main conclusion. Changing magnetic field through a coil, basically flux through a coil, when it changes, it produces electricity. Great. If I move the bar magnet slowly, the electricity produced is less. But if I move it fast, the electricity deflection, you can see, is also large. Okay, perfect. If I move the north pole towards the coil, then you can see the deflection is one way. If I move it away, it is the other way. Observe now. I'll move the north pole towards the coil, it deflected like this, left side. If I move it away, the deflection is right side. It shows that, the manner in which the field changes also decides the polarities, the direction of the current. So that was another thing. Also, instead of one turn, if I use two turns, the electricity produced will be double. Observe this. There is only one turn. I move this, it deflected so much. I move this, it deflected so much. Instead, I make two turns. Observe now. Wow, it deflected more. I make 4 turns. Observe now. Wow, so much of deflection. So the deflection is proportional to the number of turns. More the turns, more number of times the field lines will pierce through the coil again and again. One coil, then second coil, then third coil. So you will see more electricity will be generated. So it is definitely proportional to that. Not just that, if I make the area small, observe it now, and if I move the magnet, so much deflection. If I increase the area, more field lines are piercing through the coil. They are entering through the coil. Observe, the deflection is more now. The deflection is more the moment the area increases. The moment the area decreases, the deflection is not so much. The deflection is not so much. So definitely it depends on the area. It depends on which polarity is going towards it. It depends on whether it is going towards or going away. It also depends on the number of turns. Can we move the coil? Yes. Even moving the coil will produce the deflection. I don't know whether you can see the deflection. Rather, I'll keep a bulb so that you can see it. Even if I move the coil, do you see the bulb is glowing? Can you see the bulb glowing, guys? Can you see the bulb glowing? So what does it say? Either the magnet moves or the coil moves. Either way, electricity will be produced. See this. See, electricity is produced. The bulb is glowing. So relative motion between the magnet or the coil, will produce electricity. This phenomena is called as electromagnetic induction. What a beautiful way to understand this. That was the first experiment. The second experiment was like this. Instead of a bar magnet, they used an electromagnet. Actually, wait. They used an electromagnet. Basically, they replaced the bar magnet with a current carrying coil. Don't you see this is behaving like a magnet? Yes or no? Keep it on the chat box. Did you see this current carrying coil is behaving just like our previous bar magnet? There is no difference. So the observation should be exactly similar. So if I move this, again you will see the bulb is glowing. Again you can see the bulb is glowing. If I even reverse the direction of the voltage, immediately the fields which are going like this now will go like this. So the flux through this will change. The field through the coil will change. Observe, it will glow. See, it is glowing. See, it is glowing. See, it is glowing. I will place it nearer so that you can see it very easily. See, why is it glowing? Because the direction of the current will change, field will change, the flux direction will change, so the current will be produced. Any flux change causes, any kind of flux change will cause electricity in it. And you can see all those previous observations. If I increase the number of loops, obviously the electricity produced will be also more. If I reduce the number of loops, I will see the electricity produced will be slightly less. If I decrease the area, then the electricity produced will be again less. If I increase the area, then I will see again the electricity produced will be definitely more. All those previous observations are still going to be valid. So that is what is basically explained in these two experiments. This was the first experiment. This was the second experiment. Is this absolutely clear? Two experiments clear? Write it down. Krishna, Madhumati, Tanuja, Jasmine, Suchi Mama, everyone. Absolutely. Very good. Third experiment. About two experiments involved in relative motion, magnet and a coil between the two coils. Through another experiment, Faraday showed that relative motion is not an absolute requirement. Shows that two coils C1, C2 held stationary. C1 is connected to a galvanometer while the second is connected to a battery. It is observed that galvanometer shows a momentary diffraction when tapping the key is pressed. The pointer in the galvanometer returns to zero immediately. If the key is held pressed continuously, there is no deflection at all. It is observed that galvanometer shows momentary deflection when the tapping of the key is pressed, and it returns to zero immediately. If the key is held continuously, there is no deflection in the galvanometer. When the key is released, again a momentary deflection is observed, but in the opposite direction. It is also observed the deflection increases dramatically when the iron rod is inserted in the axis. Okay, so what was the third experiment? Basically, it is about this only. See, imagine it is 0 volts. You turn on the switch. meaning this circuit gets connected. The moment you turn it on, do you see there was a momentary deflection in the galvanometer? If you didn't see, I will show it to you again. Just one second. 0. Observe the galvanometer. Right now the circuit is off. I will turn it on. See, there was a small deflection. Maybe you could not see it so easily. I'll do one thing. I'll bring this closer. I will increase the number of loops so that you can see the deflection very easily. I'm turning it off. I hope you saw the deflection. I will turn it on. See, there was a deflection. I will turn this circuit off. Again, there was a deflection. I will turn this on, deflection, but it goes off the moment it is on. Why? Because once the circuit is on, even the current is flowing, even though there is magnetic field, that magnetic field is not changing. That is why there is no current. But the moment I turn it off, see, there is a deflection. Why? Because suddenly there is a change in the flux. So, observe which direction does this galvanometer deflect. When I turn on this circuit, it deflected this way. When I turn off this circuit, it deflected the other way. It shows that again the current will reverse the direction when you do the exact reverse activity. Basically, when you turn on the current, the field might increase here, so the deflection might be here. When you decrease the current, the flux is changing in the opposite direction, so it will deflect in the other way. So reversing the activity reverses the current, reverses the deflection. That is what is being noted down over here. Is this absolutely clear, my dear warriors? All the 3 experiments? Yes, perfect. So these were the 3 experiments. After this, you will never ever forget what exactly happens. Then they talk about magnetic flux. I will just block the results and I will just explain this once again to you. We have discussed about magnetic flux in the previous chapters also, which is BA cos theta. This is just a reminder of it. Faraday's, he called magnetic flux is defined the same way electric flux is defined. Magnetic flux through a plane of area of A placed in a magnetic field is given by this, where theta is the angle between magnetic field and the area. And if the magnetic flux has different magnitudes, different directions, then you do summation or integration. The unit of magnetic flux is Weber or Tesla meter squared. Magnetic flux is a scalar quantity. Here they are given these diagrams. I'll just remind you of this. Imagine you have, let's say, an area over here versus an area over here. Let's say here some magnetic field lines are passing through it. Here maybe more number of magnetic field lines are passing through it. Then I will say that this area is allowing more field lines, less field lines. So this is less amount of flux. This is basically more amount of magnetic flux. And this flux, this magnetic, B stands for magnetic flux, is given by B dot A. So it is basically your magnetic field dot producted with our area vector. Magnetic field dot producted with our area vector. That is your magnetic flux definition. More the field, more the flux. More the area, more the flux. Also angle matters. So what is the direction of this particular area vector, you might ask. So if this is the surface, the perpendicular drawn to it gives me the area vector, the perpendicular. If this is the surface, the perpendicular drawn to it gives me basically the area vector. So the angle between area vector and the magnetic field is basically theta. Area is a vector quantity when it is shown as a perpendicular to the surface itself. Perpendicular to the surface itself. Magnetic field is measured in Tesla. Area is measured in meter square. So that Tesla meter square is exactly a Weber. A Weber is nothing but Tesla into meter square. That's what they have mentioned over here. Now here the surfaces are flat, but what if the surfaces are not flat? Then what do you basically do? Say for example, and the field is also not uniform everywhere. Then you basically divide it into small areas, and you find the flux through each of such small areas, something like this. I'll just show it over here so that you get an idea of it. Imagine this is a curved surface, so area vectors at every point are in different directions. The fields might be also in different directions. So maybe I'll show some of the magnetic field lines over here, some random magnetic field line over here. So that magnetic field is B. That area vector will not be A, rather it will be dA. There will be some angle between them. Every point the magnetic fields will be also different. So the small flux, so the small amount of flux passing through that small area which I have considered over here, that small area, right, this particular small area which I have considered over here will be d phi, and that d phi will be nothing but the magnetic field dot the small area vector. So therefore the total flux phi will be integral of d phi. Integration means summation, that means addition. Therefore that total flux will be integration of our magnetic field dot area vector. Our magnetic field dot area vector. Is this absolutely clear? How we find the total flux for a curved area for random magnetic field? Everyone, you understand why integration came instead of summation? Because the integration is just like summation but for small quantities, for small things. Great, that is what they have explained over here. Alright, so let me just block this also. If the magnetic field has different magnitudes and directions at various parts, then the entire thing is given via basically integration. Okay, great. So that was this particular slide. Moving on to the next slide, guys, coming up on your screen. Okay, now Faraday's law of induction. Faraday arrived at a conclusion: the EMF is induced in the coil when the magnetic flux through it changes with time. So what was the conclusion? Faraday arrived at a conclusion that EMF is induced when there is magnetic flux which is changing, and all these were supported by his observations during his experiments. So all those experiments, observations are mentioned over here. All right, and from that he creates a final formula. All the experimental results are mentioned in this particular paragraph. No need to memorize this. There is nothing important there. Whatever I showed you, right, the same things are mentioned over here. Okay, the Faraday's law is stated as Faraday's law of electromagnetic induction. Faraday's law of electromagnetic induction, which says that the magnitude of the EMF is equal to the rate of change of the flux through the particular circuit, and the formula for this is exactly this one. EMF which is induced is d phi by dt. I'll come to it why minus sign, just to show you what they have written in this paragraph. He says that the faster you move the coils, more the number of turns, what happens? You can see more field lines will pass, or more field lines will change within this coil in which electricity is generated. So how quickly the flux changes decides how much deflection or how much electricity is generated. If it is not changing so much, then the electricity generated is also not so much. But if it changes really fast, then the electricity generated is also more. So flux change, how quickly it happens, decides the electricity which is generated. Electricity generated, the other word for it is electricity induced. But you need to measure it with something, either amperes or volts or something. So we measure it in voltage, volts. So the electricity generated is called as the EMF which is induced. Why the word EMF? Because see, there was no battery connected to this, but me moving this coil has created electricity in it, so it is behaving like a battery. It is behaving like a battery. Just the main difference is, in a normal battery, chemical energy in the battery gets converted into electricity. Electrolytic elements are there which generates electricity. Here it is generated because of the phenomena of induction. This coil is inducing electricity in it. This coil is moving electricity in it. Yeah. So it is like Pandu, guys. This coil, no, is like Pandu. This coil is like Champa. This Pandu is where the electricity will be generated. This Champa, if she is standing over there, Pandu is not getting entertained. No entertainment. See, Pandu, is he getting entertained? No. Champa moves. She dances. She dances. So then this coil will also get entertained. This coil will get entertained. Wow, very nice. Champa stops? No. Champa dances faster. Tak, 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 dang, ding, dang, 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 doom. That's it. The coil will get entertained. So that is exactly what is happening over here. So that's what Faraday also says. The observations in the form of the Faraday's law of electromagnetic induction, the magnitude of the EMF induced in the circuit. This is our Pandu. The magnitude of the induced EMF in a circuit. So Pandu's entertainment is proportional to how quickly Champa is changing the flux. How quickly there is rate of change of magnetic flux in the circuit. Understood, guys? So this is Pandu, this is Champa's dance. Champa is at rest, phi will be constant. Champa is just like this. Pandu is like, what are you doing, Champa? Change. So Champa dances. So Champa dances. So d phi by dt. d phi by dt will come, EMF will be induced. EMF will be induced. Pandu will get happy. Wow, very good, Champa. Champa dances fast. Pandu will be like, wow, very good. That's what happens. Why this minus sign? We'll come to it in a later on point. It is because of Lenz's law. Okay. So, before going there, let me talk about this N first. If there are N number of turns in that secondary coil, obviously you will see that more EMF will be generated because more flux will pass. So this N will come only for the sake of showing that there are more number of turns. So I'll just mention that in the case of a closely wound coil of N number of turns, the flux will be also, at a higher value. So the induced EMF will be increased by the number of turns. Hence you multiply N with it. Hence you will multiply N with it. Very good. Everybody understood. So everybody needs a Pandu and Champa in the life to understand any kind of complex law in physics. What is that negative sign? Let's talk about that negative sign. The negative sign indicates the direction of the EMF and hence the direction of the current in a closed loop. This will be discussed. See, they are also saying we'll discuss this later. Okay, we'll discuss this later. Anyways, now the flux can be also altered by changing the shape of the coil, rotating it. In these cases too, EMF is induced. All right. Okay. So how can you change the flux? Observe this. See, if I want EMF to be induced, that means I 100% want the magnetic flux should change. Only then EMF will be induced. How can I change the magnetic flux? There are only three different ways. There are only three ways by which I can do it. What are those three ways? Observe. First way is, imagine my magnetic field only changes. Magnetic field changes. Meaning, imagine I bring the bar magnet close to it or away from it. So magnetic field changes. So this way flux will change. And this is exactly what we have been seeing over here. I'm bringing the magnet close or far away, EMF is induced because the field passing through it is definitely changing. The flux is changing. So now it is becoming strong, now it became weak. Now it became strong, now it became weak. So flux change definitely causes the EMF to be induced. The second option is because flux is B into A into cos theta. I can change B, I can change A, or I can change theta. So next is changing the area. So the next is basically area itself changes. Imagine guys, there was a coil like this. It is held like this. Now it has some area. Now imagine I do this. Area has increased suddenly. Area has increased. I do this. Area reduced. Imagine this. I make it like this. Area reduced. Now area increased. So imagine magnetic field lines were passing through it. Okay. Now there is less flux. I make more flux. Less flux, more flux. Won't electricity be generated in this? Obviously. So changing the area also will change the flux, hence creating electricity. The last thing is basically changing the theta. Theta changes. Theta basically changes, which makes sense. The coil was like this, I change the orientation, change the orientation, change the orientation. Immediately you will see electricity will be generated in it. Is this absolutely clear? That is exactly what has been mentioned in this particular paragraph. That is exactly what is mentioned in this particular paragraph. Shall we now start seeing some questions, guys? That will be better. Okay, so let's see. There is a square loop of certain side and resistance. It is placed in the east-west plane. East-west plane. A uniform field is set up across the plane in the northeast direction. North to east, not northeast. North to east. Magnetic field is decreased to 0 in 0.7 seconds as a steady rate. Determine the magnitudes of the EMF and etc. All these things. They have done the calculation. So basically, let's understand what is this. First, let me place my coil. This is our coil, guys. This is our coil, like this. It is vertically. It is in the east-west vertical plane. The magnetic field is in the northeast, my bad. It is slightly different. North to east direction, the vertically in the east-west plane. Okay, so basically it means this is our east, this is our west, this is vertically upwards, this is vertically downwards. If you go inside, it is north. It is north. If you go inside like this, that is basically your north direction. If you walk inside the plane or towards the board. Okay. Now, if you look at it from the top view, the same thing, that coil's only top part will be seen. The coil's only top part will be seen. And then you will realize, okay, this is the north direction. This is the east direction. This is the east direction. This is your west direction. And obviously, like this, towards you will be basically vertically upward. And down will be over here, inside the plane of the board. This is basically your top view. Are you able to visualize this coil first? Yes or no? Give me a thumbs up. Are you able to visualize this coil? Hi Disha. Yeah. If you are able to visualize this coil, then you will be able to do it, because otherwise whatever they have done over here, right, will be very, very difficult to understand. Where is the magnetic field? The magnetic field is in the northeast direction. I cannot show it here so easily. It's a little difficult. This is north, this is east. So the magnetic field is actually going at an angle, guys. The magnetic field is actually going at an angle northeast direction. So basically this angle which you are seeing over here is nothing but 45 degrees. And if you talk about the area vector, this exactly is our area vector, perpendicular to the plane. So area vector is actually inside. Area vector is inside. So when you see from the top, you will see it sticking outside like this. So this north direction is our area vector. So the angle between area vector and the magnetic field is 45 degrees. Is this clear, everyone? Visualizing this? Okay. So now, as per this, you can see that the field is set up across the plane. The field is decreased to 0 in 0.7 seconds. So if you talk about initial field, it will be magnetic field into area into cos theta. Magnetic field will be given, I think, 0.1 Tesla. Area of the coil, square of loop side 10 centimeter. If the loop side is 10 centimeter, what will be the area, guys? 0.1 meter into 0.1 meter, which is 0.01 meter square. So put the area as 0.01 meter square. Cos theta, it is cos 45 degree. What is cos 45? 1 by root 2. So this will become 10 to the power minus 3 by root 2 Weber. That is your initial flux. What about the final flux? What is the final flux? It is decreased to 0. That means no field only, 0, nothing. So definitely it has changed. Can you see? There is definitely change in flux. There is change in the flux. How much time it took? 0.7 seconds. So 100% there will be EMF induced in it. And the induced EMF magnitude is how much is your change of flux upon the time taken. Why is there no minus sign? Because here there was minus sign. I am just interested in the magnitude, the modulus. So I'm not worried about the sign. I've put mod symbol also. How much is the change? This minus this. So basically 10 to the power minus 3 by root 2 minus 0 upon how much is the time taken? 0.7. 0.7. Is this absolutely clear, guys? Yeah, and in ideas I'll come to the EMI lesson also on the JEE channel. Don't worry. Yeah. Now, actually speaking, this 10 to the power minus 3, 1 by root 2 is actually 0.7 approximately. So you will see approximately it is 10 to the power minus 3 volts, which is basically 1 millivolt. You can see approximately it will be 1 millivolt. Yes, it is correct. Approximately 1 millivolt of electricity is generated in this coil because you removed the magnetic field. Now the another question is also there, which is about current. How do I find the current? Guys, the current which will be created will be the EMF which is generated divided by the resistance of that particular coil. Oh, Ohm's law, E is equal to IR. I will be E by R. So EMF is 1 millivolt. Resistance, is it given? 0.5 ohms. 1 by 0.5 is 2. So it will become 2 milliampere. So the current which is induced is approximately 2 milliampere. I hope this is absolutely clear. Yes. Everybody? Now some of you will be like, sir, what about the Earth's magnetic field, sir? Why is that not considered? Can somebody tell me the answer in the chat box? Why did we not consider the Earth's magnetic field while making these calculations? Can anybody tell me in the chat box? There is a reason for that, and the reason is it was never changing. It was always constant. Yeah, so that's the reason for it. So the Earth's magnetic field is also producing a flux, but it is a steady field which does not change with time. Hence, it is not going to be considered. It is not going to induce anything. That's the reason for it. Next, there is a coil of some radius, 500 turns, some resistance. In its perpendicular plane, there is a horizontal component of the Earth's magnetic field. It is rotated, theta is changed by 180 degrees in 0.25 seconds. Estimate the magnitude of the EMF and the current which is induced in the coil. Horizontal component of the Earth's field is given to be 3. There is a circular coil, these many turns, this many ohms. In its plane is perpendicular to the horizontal component of the Earth's magnetic field. Okay, let's understand what exactly is happening. This is the coil. This is the coil, guys, simply put. This is the plane of the coil. The plane of the coil with its plane perpendicular to the horizontal component. Okay, so I need to take, oops, I can't do that. So think of this as your area vector. The plane of the coil is perpendicular to the horizontal component. Horizontal is like this. This is horizontal. This is vertical. So this is the Earth's magnetic field which is given to me. The Earth's horizontal magnetic field, which is 3 into 10 to the power minus 5 Tesla, that is given to me. Now what is done is this coil, I hope you understood, this coil is basically having its plane which is perpendicular to the horizontal component. So the area vector will actually be in this direction only. Area vector is parallel to the Earth's magnetic field. Now what you do, you have rotated the coil by how many degrees? It is mentioned 180 degrees. So which means that coil will now be basically like this. The area vector is now right like this. This is where the area vector is. Obviously the Earth's magnetic field is still, in this direction. There is no change in that. So in this process, theta has changed. Theta has changed. The angle between area vector and the magnetic field has changed because the coil was turned by 180. So the area vector also has turned by 180 degrees. So obviously flux change has happened. So let's calculate the initial and the final flux, and then we can find the magnitude of the EMF and everything else. If you ask me, what is the initial flux? I'll be like, it is BA cos 0. What is cos 0, guys? Cos 0. Why 0? Because it is 0 degrees. Cos 0 is 1. Magnetic field is already mentioned. 3 into 10 to the power minus 5. What about the area? Radius is given to be 10. Turns is 500. Oh, so I also need to multiply it with the number of turns, or else I will be making a mistake. So pi into 0.1 square multiplied by 500. Very, very important. Pi r square is the area into 500 because there are n number of turns. So each turn will create that flux. So into n also needs to be done. Okay. 3 into 5 is 15. Pi as it is. 10 to the power minus 5, 10 to the power minus 2, 10 to the power minus 7. And these two zeros, actually they will cancel. So into 10 to the power minus 5 Weber. That is your initial flux, guys. If you ask me about the final flux, it will be B A cos 180 degrees into n. So the same thing, but with a minus sign, because cos 180 is negative. So it will be minus 15 pi into 10 to the power negative 5 Weber. So that is your final flux. So definitely there is a change of flux from positive to negative. So that change will produce that electricity. So let's go to the EMF which is induced. The EMF which will be induced, which is that change in the flux upon the time taken. I'm only interested in the magnitude. This minus this, guys. So 15 pi minus 15 pi. That's the change. The whole thing into 10 to the power minus 5. Whole thing divided by the time taken. Time taken was 0.25 seconds. 0.25 is 1 by 4. So 4 goes on the top. 15 pi minus becomes plus. So it will become 30 pi into 10 to the power minus 5. 4 3s are 12. 1 0 will go. So 12 pi into 10 to the power minus 4 volts. That is the answer for the EMF which is induced. If you want, you can also find the value of it. So it should be basically 12 pi, which comes out to be 3.8 something. 3.8 into whatever. Yeah, 10 to the power minus 3. Is this absolutely clear, guys? Yeah, 12 pi into 10 to the power minus 4. Once I get the EMF, finding the current is not that difficult. The induced current will be the induced EMF upon the resistance of that coil, which is 12 pi into 10 to the power minus 4 volts by the resistance, which is 2. So it will be basically 6 pi into 10 to the power minus 4 amperes. That is your induced current. EMF by R. That's it. Clear, guys, how to solve these kind of questions? Main problem was n. Many people forget the number of turns. If you forget n, everywhere that factor of n will give you a wrong answer. Everywhere. Second thing, angle between the area vector and the magnetic field. If you make a mistake there, again another problem will happen. If you think it was perpendicular, sir, it was perpendicular, angle is 90 degree. Cos 90 will give you 0. The answer will be 0 then. So we will make another mistake. So the plane of the coil is perpendicular, but area vector is perpendicular to that also. So ends up being parallel. Area vector ends up being parallel to the field. That is another common mistake. Diamond clear? Very good. Awesome. Clearo. Perfecto. Hi, Virat Vishnu. Welcome aboard. All the new students who are watching the class, make sure you are commenting, liking, subscribing to the channel. So you have seen all the ways, guys, how magnetic field changing, area changing produces. Here the magnetic field changed. In this question, the area changed. How it produces, electricity. What about theta change? We'll come to it towards the end. Don't worry. Theta changing concept will come towards the end. Lenz's law. Basically, this is going to talk about the negative sign. Remember, I have told you we'll discuss it later. I told you that we'll discuss why that negative sign comes. The negative sign, it will be discussed later. So now is that later time. So Lenz's law says that how the direction of the current is decided. Yeah. Hi Nitish, thank you so much. I hope you too have a very, very bright day. Thank you so much for such a lovely wish. And all the warrior Pandus lighting up the chat box. Jasmine, Madhumati, Krishna. Thank you so much, guys. Thank you so much. Okay. So, oh yes, Krishna, I will have water. Thank you. Okay, now the direction was given by Lenz's law, the direction of the current. Lenz's law gives the direction of the EMF and the current. The polarity of the induced EMF is such that it tends to produce a current which will always oppose the change in the flux produced in it. Negative sign just shows that particular effect. That negative sign actually shows this particular effect. We can understand Lenz's law by examining experiments, etc. And to counter, they have explained it. I will explain this to you, don't worry. Now consider the bar magnet will be attracted. This violates the law of conservation of energy and hence that cannot happen. Okay, this dissipate by as per the Joule's law of heating. Okay, and then they have given one example over here. Okay, so let me bring back our experimental setup. Let me bring back our experimental setup back over here. Now, as you can see, my dear warriors, over here, this bar magnet right now is not creating any electricity over here. Which direction will the current flow is decided by how which polarity is moving in which direction. Right now, the north pole is coming towards the coil. You can see a current is created in this particular coil. As you can see, as I move this bar magnet, a current is created in this coil. If I move it in the opposite direction, the reversal of current happens. The reversal of that particular current, definitely it happens. I'll increase the loops so that you can definitely see it very clearly. So, how is this current direction decided? See, imagine when I move this bar magnet, there is a current moving in this coil. This current will also create a polarity. This current will also create a magnetic effect. It will produce its own magnetic field. Not this, guys. This current will have its own magnetic field. This will also behave like an electromagnet. Agree or disagree? Me moving this, there is a current which is created. So naturally what will happen? There will be a north-south, south-north polarity which will be created because of this coil only. This coil's current. Right now there is no polarity because there is no current. But when I am moving it, while I am moving it, there is magnetic polarities which are created. How will that polarity be? Just imagine, when I am bringing this magnet close, if there is a south polarity here, north polarity here, this is south, this is north. Will this magnet be attracted or repelled? Put it up in the chat box. When I am bringing this magnet close, if there is a south polarity here, north polarity here, south here, north here, what will this electromagnet do to this permanent bar magnet? Tell me, will it attract it or will it repel it? While I am bringing it close, what do you think it will do? It will attract it. Yes, correct. South attracts north. South repels south. Everybody, very good. Which means, imagine if I push this magnet will get attracted by this coil. If this magnet gets attracted by this coil, won't this guy's kinetic energy increase? Won't this getting attracted increase its kinetic energy? Wow. At the same time, electricity is also getting generated. So electrical energy is being generated, kinetic energy is getting increased. Who is giving this energy? Think, is Pandu giving? Is Champa giving? Is some bond being broken? Is something else happening? The answer is no. From nowhere, you are creating kinetic energy and electrical energy. This is violating the principle of conservation energy. This should not happen. Hence, whatever we assume is incorrect. So actually what might be happening is, when I am moving it over here, the north polarity is created here, south polarity is created here. What will north do to north? What will north say to north? Why are you coming? Repel. So it will decelerate it. It will, this coil, this magnet which was moving fast will start slowing down. It will start slowing down. Earlier it was moving fast, now it will slow down. So where is the kinetic energy going? That kinetic energy is going into this coil's electrical energy wirelessly. Imagine wirelessly energy getting transferred to something else. That's the beauty of electromagnetic induction. Got it? Everybody with me on this? Absolutely clear. So the polarities of the coil in which electricity is induced in such a way that it always will oppose the change. It will always oppose the change. Right now, while I was bringing this magnet here, there was a north created here, south created here, asking the magnet to stop. But if this bar magnet is going away, then current will also reverse, meaning the polarities will reverse. So when I take this bar magnet away, you will see a south polarity will be created here, north will be created here. What will south say to north? Come to me, come to me. Yes, so as you push this magnet away, it will start slowing down, it will decelerate. Again, the kinetic energy gets transferred into the coil's electrical energy. Again, the kinetic energy is getting lost and converted into electrical energy, which obeys our principle of energy conservation. This is exactly what happens. So, looking at this behavior, it feels like, sir, you know, my elder brother and sister, sir, anytime I want to go out, no, they will be like, no. Why are you going out? Stay at home. Sir, when I tell, today I am going to stay at home and enjoy my day, then my brother and sister, why are you staying here? Go out. I want my friends to come over here, you get out of the house. What is this, sir? Whatever I do, every time opposition, sir. Today I thought I will sit and study. I got one nice scolding, sir. Why do you want to sit and study today? Go out and play. What is this? If I say that today I want to go play with my friends, no, you come sit and study. Every time opposition, whatever I do. If I say I want to dance, don't dance. If you say I don't want to dance, dance. So this is exactly what Lenz's law is. If this magnet comes here, this coil will be like, why are you coming close? North pole. North pole, North pole, repel. Okay, it stops. If this goes away, South pole. Oh, come. Why are you going away? So, you know, every time the behavior is to oppose any kind of change. If it tries to increase, it will try to decrease it. If it tries to decrease, it will try to increase it. Always oppose. Always oppose. That is exactly what Lenz's law is. Else it would violate the conservation of energy. Else it would violate, this would violate the conservation of energy, which cannot happen. So Lenz's law is based on the conservation of energy principle, nothing more. And that is exactly what you should understand. So let's try to see some examples over here. Let's try to see some examples over here. shows the loops of different shapes moving in or out of the region of a magnetic field which is directed into the plane. What are these crosses showing? Magnetic field. Where is it going? Cross means going away from you inside the plane of the board. Dot means it is coming towards you. Okay. So, this coil is coming in, this coil is going out, only this much region is magnetic field region. This coil is again going out. All right. Fantabulous. So, oh, thank you. Yes. So, let's shade the region where the flux is present. Here. Oops. Whatever region I am shading, that is where the flux is right now present. Later on, that will also change because they are going either in or out of that zone. Are you able to see that? Are you able to see that regions which I have shaded, guys? Okay. Great. Determine the direction of the induced current in each thing. Tell me, as this rectangular loop comes in, will the flux increase or decrease? Tell me clearly, guys. Will that flux, because now as soon as it comes in, this much part will also be inside. So won't the flux increase, guys? If the flux increases, but where does it increase? It is going inside. The flux increases inside. What will Lenz say? Why are you increasing? I will try to reduce you. So, the induced magnetic field will be opposing it. Induced magnetic field will be towards you. The induced magnetic field will try to weaken it. It will try to weaken. It is trying to weaken it. Because it is increasing inside, it will try to weaken it. Now, if the magnetic field line is coming towards you, take your thumb, put it towards you. See how the fingers are curling. See how the fingers are curling anti-clockwise. So the current in this particular coil will be in this anti-clockwise direction. So an anti-clockwise current is being induced over here. Is it clear how Lenz's law has to be used? It's very simple. See whether it is trying to increase or decrease. Oppose that change. That's all. Absolutely. Let's go to this one over here, or even this one. Tell me, as this or this coil is trying to go away, next instant the flux will only remain in this much part, because this much part would have gone out of the field. So in these two, what is happening? In these two, what is exactly happening? Obviously, the flux is decreasing. The flux is decreasing inside. So because it is decreasing, what will the induced field say? What will the induced field say? The induced field will be like, wait a minute, I will support you. I will strengthen you. I will strengthen you. Strengthen you means field should be inside. Field is inside, take your thumb, put it inside the plane of the board, see how your fingers are turning. Clockwise, guys. So you will see a clockwise current which will be set up inside. A clockwise current. Even here, the induced current will be in the clockwise direction. So, yeah. Current flows along BACB and here also the same thing that they have mentioned. Now magnetic flux decreases, okay. There are no induced EMF as long as the loops are completely inside or outside. Okay, there is one peculiar case which I want to discuss. Tell me what would happen if I made another new loop over here. If I made another new loop over here and this loop is traveling here. Tell me, guys, in this particular loop, which direction will the current be induced? It's completely inside. Because it is completely inside, you know what happens? Whether that loop is here or just after some time, maybe that loop reaches over here. Just maybe after some time, the loop reaches here. Tell me, has the flux changed? Tell me, has the flux changed? No, right? So basically, that flux, for that, the flux is constant. The flux doesn't change. So because of that, what will happen? Induced current will be also zero by Faraday's law. There will be no current only. That is exactly what they have mentioned here. If there is the loop is completely inside or outside, then there is no current which is induced. If there is no current, that means the loop is completely inside or completely outside. It is not entering in or nor is it exiting out. Okay, very, very important conclusion. Great. Now that we have studied till here, let's go to the next part, which is basically your motional EMF. Motional EMF. Here, I'll explain to you very simply in a very easy manner. There is a wire which is bent in the form of a C shape. This is the alphabet C. This also looks like C. So imagine you take a long wire and you bend it in the form of C. So that is why it is called as a C-shaped wire. On that, you take a rod and such that it is touching at both the points on the C-shaped wire. There is magnetic field also in this region. Okay. Now what happens is, imagine this rod is here. So if you measure this particular area, this is the area which will give me flux within this coil. This is like a coil. There is some flux passing over here. After some time, just imagine this same rod reaches over here. This is after some time. Okay, just after some time, the same rod maybe reaches here because of some motion, because of some velocity. So what will happen now? What will happen now? If you measure the flux, it is only through this much part. It is only through this much part. Can you see this much part has gone away? So definitely this part corresponds to the change of flux. Change of flux. And what does change of flux give you? If there is a change of flux, there is definitely EMF which is induced. And why did this happen? This happened because of the motion of the rod. Motion of a conductor. Motion of a conductor. So a moving conductor in a magnetic field created electricity, generated electricity. Hence the name given motional EMF. Motional. Due to the motion, there is EMF. Hence motional EMF. Is this absolutely clear? Everybody? Okay. That is exactly what this is. So, they have mentioned it over here. The value of this EMF, that is the main formula which you should know. Derivations and all that not needed at all. So, the value of the induced EMF is given by magnetic field into length of the conductor into the speed. Magnetic field into length of the conductor into the speed, the velocity. So, the induced EMF BLV is called motional EMF. We are able to produce EMF by moving a conductor in a magnetic field. In a magnetic field. I hope this is absolutely clear. Everyone? Okay. So, imagine this. This explanation and all that is not needed. Don't worry about it. I'll explain it to you in a bit. Don't worry. Imagine this is the axle of a vehicle. This is the wheel. This is the wheel. Okay. It is going on a road. It is just going on a road. Imagine Earth's magnetic field is there and Earth's magnetic field is like this. This is the Earth's magnetic field. This is your wheel. This is the axle. And the axle is having some length L and it is moving with some speed. Don't you see that axle, since it is moving with some speed, between the ends of the axle, there will be some EMF which is generated. That EMF which will be induced in that particular axle will be given by B into L into V. If you measure approximately Earth's magnetic field is of the order of 10 to the power -4, -5 Tesla. Let's take a slightly stronger point. Let's take 10 to the power -4. Length, maybe it is around 2 meters. Maybe you are going with 20 meters per second. Okay, this is 2 meters. This is 10 to the power -4 Tesla. This will become 2 2s of 4, 0, and this will make it 10 to the power -3. So which is around 4 millivolt. So imagine when you are driving a car or a truck, imagine between the two tires of the truck there is a electric voltage which is created, EMF which is developed, but it is very, very small. 4 millivolt is not much. 4 millivolt is not too much. You need a very long axle or you need very large speed so that you can create enough electricity. Sir, what about bullet train, sir? Sir, bullet train will go. Or sir, what about a jet, sir? Fighter jet. Fighter jet has a long wing, and it has got large speed also. Will the electricity generated in that be more? Yes. So instead of 2 meters, make it 10 meters. Instead of 20, make it 100 or 200. So you can see it will increase by a factor of some 100 times or something like that. So instead of 4 millivolt, it will become 400 millivolt. Still it is 0.4 volt. It is not much. It is not much. So you can see the EMF which is induced is there, not much, but it can create some undesirable effects in some places. Trisha, no issues. Watch the recorded class because we had a lot of fun today, lots of animations and simulations for visualization purpose. Okay, watch the recording. All those who are joining in late, no worries. Yeah, but please make sure that you watch at least the recording. Okay, don't miss the class. It's a very interesting class. So electricity is created even in a moving train, moving axle, fighter jet because of the earth. So, this gives weird ideas. So, I can generate electricity from moving objects, and that's exactly what happens while you are trying to generate electricity in a generator, in a hydropower plant, in a nuclear power plant. They use moving coils, moving conductors to generate electricity. Another such example is of a rod which is rotating, not translating, rotating in a magnetic field. Imagine I take a rod and I'm rotating it like this. Then how much electricity is being generated inside of this? How much electricity is being generated inside of this? So this is a very important derivation which you should know. Imagine you take this conducting rod whose length is basically L, and it is known to me that it is in a region of magnetic field like so. This is the region of your magnetic field. This rod is rotating, it's hinged over here. It is rotating like this with an angular speed omega. Now what happens is, in this particular diagram, you will see every point has a different velocity. So here the speed is less, here the speed is more, here the speed is even more, here the speed is even more. So the EMF generated will be also different at different points. If you take a small section of that rod, okay, if you take a small section of that rod which is at a distance of x, whose width is dx, whose velocity is v, there is a small EMF which is generated in it. I will call it dE. There are many such things. So think as if there are many batteries till the end. Many batteries till the end. From the start till here. So this rod is small EMFs arranged in series. So this rod altogether will behave like one single battery whose EMF induced is E induced. And the question is, how much is this E induced? That is what we need to find. So obviously there is integration over here which is involved. If I find D, my job is done. But to find that, I need to know the speed. By circular motion, we know velocity, radius and omega. They are related. So V will be nothing but omega into x. V will be nothing but omega into x. Omega r, so omega x. That small EMF which is generated, the EMF induced in the element, in that particular element, using the formula BLV, L is dx into V. So it will be B, velocity was omega x and dx over here. That is your dE. But I don't want dE, I want the total EMF. The total EMF will be integration of all this dE. The dE is nothing but B omega x dx. So I have to integrate this to get the total EMF. B and omega are constants, only x and dx will remain inside starting from 0 to L. X starts from here when x is 0. When x goes till here, the value of x is the length of the rod. So integration of x with respect to dx is nothing but x square by 2. So it will become L square by 2 minus 0 square by 2 after putting the limits inside. So it will become B omega L square by 2. That is the induced EMF. That's exactly the formula which you need to use to solve this particular question, guys. B omega L square by 2. If you substitute omega, substitute field, substitute the length, you will get it. Okay? I hope this is absolutely clear. Absolutely clear. Everybody with me? Okay? Perfect. Now there is one important point which is mentioned over here. Let me stress on it a little bit. If there are more spokes, then what will happen? So imagine there is one conductor here, another conductor over here. Okay, imagine these are the conductors and all these three conductors together are rotating like this. There could be 4 or 5 also, doesn't matter. Then will there be EMF generated across every one of them? The answer is yes. Every part of that rod will behave like an independent conductor. EMF induced in each of them will be half B omega L square. Same EMF here, same EMF here also. So now if you measure the EMF across this point and this point, this point and this point, this point and this point, each of them will behave like a battery but in parallel. Yes, understand this. Very important, guys. Each of them will behave like a battery but in parallel, like this. This is your common point. This is your common point. And all these outer points, you can think of them to be at the same potential, guys. Very important. So it's like all these outer points are at the same potential. Perfect. So therefore they behave as if they are in parallel. They behave as if they are in parallel. This point, this point, this point. They are all connected as if, you know, at the same voltage. So they are in parallel. So hence this diagram will be as good as saying you just have 3 batteries like this. And when batteries are in parallel, they behave like a battery in this particular manner. Same EMF. So once they are in parallel, the EMF does not increase nor decrease. It will be the same. There is no difference at all. Okay, it's just that the internal resistance will be different. If this has an internal resistance R and R, they are in parallel. This internal resistances are in parallel. So internal resistance will become R by 3. Internal resistance will become R by 3, but EMF will still remain E only. There is no difference in that. Is that clear, guys? Everybody? So that is the meaning of this last statement. You might get a question in NEET also or in boards also based on this particular concept. Very, very important. Clear? Shall we go ahead? Okay, perfect. Now let's come to inductance, because this is the last part, inductance and your generation. Inductance and your generation. Transformer is not there over here. A transformer is there in alternating current. Now, I'll tell you the manner in which they have explained. You might feel little bit confused. So I'll mark all the important pointers over here, of course. Electric current, okay, d phi by dt and all that. So important terminologies is term called as flux linkage, which is used to NB for a closely wound coil in such a case. The constant of proportionality is called as inductance. Okay, depends on the geometry of the coil and the material properties. Okay, the inductance is a scalar quantity. It has the dimensions of blah blah blah, given by the dimensions of flux by the dimensions of current. The SI unit of inductance is Henry. Okay, denoted by H. It is named in honor of. Okay, fine. And then there is another term called as mutual inductance, which long solenoids are there. Okay, the corresponding flux linkage is given by this. This is called as the mutual inductance of the solenoid. It is also referred to as the coefficient of mutual induction. The value of the mutual induction is given by this. Note that we neglected edge effects, blah blah blah. Okay, fine. Equality is very useful. Okay, and this is also there. Mutual inductance, this is very important. And then they have also given this formula of the induced EMF in that coil, which is important. All right, and then they talk again about self-inductance, and E is LdI by dt, where it is also called as coefficient of self-inductance. Okay, and the energy stored is half Li square. Okay, and all these things. Okay, so now all these things, guys, I'll explain this to you in a very layman terms so that you understand, because the manner in which they have explained inductance, I really did not enjoy it. So it's better that you understand my explanation, and then you can solve any question based out of it. Let's understand. Okay, imagine there is a Pandu over here. Second case, there is a Pandu again over here. In the first case, there is a beautiful Champa in front of him. In the second case, there is no Champa for him. Champa tells Pandu, listen Pandu, you have to prepare for NEET. Listen Pandu, you have to become a doctor. Listen Pandu, if you become a doctor, I will marry you. Listen Pandu, you know, if you do well in life, I'll be with you. So Champa always keeps motivating Pandu. So Pandu studies for NEET, becomes a doctor. In the next case, no Champa is there. Pandu feels that I should become a doctor, automatically everything will fall in place. I have to do this, I want to work in this hospital, I want to go to EMS, I want to treat patients. In the first case, Pandu had some external agent to give that motivation. In this case, Pandu was self-motivated. This type of effect, in case of electromagnetism, is called self-induction. Here it is called mutual induction. Mutual induction. Self-induction is like self-motivation. Mutual induction is like mutual motivation. Mutually you motivated each other. When Champa motivated Pandu, Pandu was like, wait Champa, why you also come with me to EMS? Why only I should go? Champa is like, yeah, correct. I will also write NEET exam. So they mutually motivated each other. They both studied and they went to AIIMS. Understood, guys? Same thing happens. So this was your mutual motivation. Champa motivated Pandu. Pandu motivated Champa. Here, Pandu motivated himself. So this is basically your self-motivation. Okay, perfect. But in electromagnetism, it is slightly weird because of the sign, the direction of the current which is induced is always trying to oppose that change. Is always trying to oppose that change. So imagine it in a slightly different way. Instead of motivation, okay, I will call it the demotivation. It's like, you know, Champa tells Pandu, come, let's prepare for NEET. Pandu says, I will not prepare for NEET. And Pandu tells Champa, you also don't prepare for NEET. Champa says, no, I will prepare for NEET. I will prepare for NEET. So it will now become mutual demotivation. Here, in this case, just imagine Pandu tells himself, I have to go and play. All my friends are playing. Then he realizes, no, I should not play, I should study. His thoughts were saying something, but his ambition, his aim, his desire, his goal said another thing. So it was self-demotivating himself to go outside and play. Pandu knows that, okay, someday I have to sit and study, tomorrow exam is there. But Pandu is like, to hell with it, I will go outside and play. So he has demotivated himself for studies. So this is exactly what happens in current electricity, guys. Imagine you have a coil and you have another coil over here. This coil suddenly generates some magnetic field. If there is a magnetic field generated by this coil and it is changing, then it will create an electricity inside this coil. So there is an induced electricity in this coil to oppose this guy's change. If this is trying to increase, this guy will be like decrease. If this guy is trying to decrease the current, decrease the field, this guy will say, I will increase it. So it is like opposing it and it is generated mutually. That is why it is called as mutual induction. So this is the field. This is usually called as the primary coil. This is usually called as the primary coil. And usually this is also called as the secondary coil. This is also called as the secondary coil. So the primary's field affects the secondary coil and the secondary coil opposes the changes produced by the primary. That is your mutual induced phenomena. Is this absolutely clear? Absolutely clear, everyone? Hi Akhil, Warrior Pandu. Same way, over here, imagine only a single coil is there. Pavam, that single coil, was producing its own field. What happened? The current changed in it. The current changed in it. So the field also changed through that coil. Field either increased or decreased. That coil was there. Suddenly somebody turned on that knob or something, increased the voltage. The current increased. The coil is like, oh my God, current in my coil increased. So what should I do? What should I do? Faraday. Lenz. Okay, I have to create electricity. Okay, I have to oppose it. Okay, I will oppose it. Immediately it will oppose itself. So it will oppose its own change. That is basically your self-induction. There is only one single coil. So any change in the field produces an induced EMF induced in itself. Here it is induced in the secondary. Here it is induced. Where is it induced? In the secondary. Is it absolutely clear? Everybody with me? The difference between self-induction and mutual induction. Very good. Awesomeness. Now, the formulas for each one of them. Observe it carefully. Observe it carefully. This is your secondary coil. This is your primary coil. The primary coil will produce some magnetic field. Maybe the magnetic field lines will go like this. Do you notice that not all the field lines are passing through the secondary coil? Only some of them are passing through the secondary coil. Can you see that? Only some of them are passing through the secondary coil. I hope you can see that very, very easily. Only some of them are passing through the secondary coil. If you bring this coil closer, or you increase the number of turns, or you basically put some iron core over here, then what will happen? The field will change, because iron core is ferromagnetic in nature, so it will increase the field. If I bring this coil closer here, those field lines which were being missed out, now even those field lines will pierce through the coil. If I increase the number of turns, the same field lines will pierce it again and again increasing the flux. So the flux which passes, the magnetic flux, the magnetic flux that passes through the secondary, coil, but generated by primary. Where is it generated from? The primary. Generated by the primary coil is called as the flux linkage. Is called as the flux linkage. I hope this is absolutely clear. This particular flux obviously is proportional to this particular flux which is generated in that secondary coil, right? This flux which is generated in that secondary coil is definitely proportional to the number of turns in the secondary, and also how much current is there in the primary. Basically, I will put it like this. It will definitely be proportional to the current in the primary. One stands for primary. If I increase the current here, more field will come. Obviously, more field lines will pass, so the flux will increase. Also, if I increase the number of turns in the secondary, so flux is directly proportional to the current as well as the number of turns in the secondary. Is this absolutely clear? Everybody understood this point? Great. Now, usually when we talk about flux, it's not through any one turn, it is the total flux. So obviously the total flux will be anyways proportional to the number of turns. Anyways, that is going to happen. So if I write that constant of proportionality as equal to, number of turns is a constant, I bring it inside, I just keep the current through the primary over here, this is flux through the secondary. Here, that constant which will come is called as mutual induction coefficient or mutual inductance. This is called as your mutual inductance. Very, very important. Mutual inductance. Is it absolutely clear, everyone? Everyone with me on this? Perfecto? Great. Now, a very important thing which you should know. You will be like, sir, here, this mutual inductance is when this coil is carrying current, producing field, and this coil is generating that electricity. What if I do the reverse? So very, very important statement which you should know. In the first case, this coil's field pierced through this. In the second case, this coil was generating okay, something like this. Here, this is primary. Now this same coil became secondary. This coil was secondary. Here this became primary. If you ask me, in the first case, all right, the current through this coil is related to the flux in that second coil, given by this particular constant m. Phi is m into I. Flux in this is proportional to this current, and that constant of proportionality was called as mutual inductance. Now, if I do the reverse exactly, flux is passing through this coil labeled 1, coil which is labeled 1, this coil was labeled 2. This flux will be proportional to the current in this coil labeled 2. What will be that constant of proportionality? That will still be m. It doesn't matter which coil you make it as primary or secondary. Some books initially they refer mutual inductance of 2 with respect to 1. This is mutual inductance of 1 with respect to 2. So M12 is actually M21 is actually M. It is the same thing. So it doesn't matter which coil you make primary, which coil you make it secondary. It is always going to have the same constant of proportionality. Is this absolutely clear? That is what they have mentioned in one of the parts somewhere here. M12 is equal to M21. Okay? M12 is equal to M21. I hope this is absolutely clear, guys. Till this point, understood? Okay. Now, what does this mutual inductance depend on? Obviously, like I told, if I bring this coil close, far away, put some magnetic material, the flux will change. So it depends on the geometry, the shape, the size, distances, etc. Shape, size, etc. It also depends on the materials which are placed inside. It is also a scalar quantity. It is also very important. It is a scalar quantity. Not just that, if you talk about the unit part of it, this M is Weber divided by current. So a Weber divided by ampere is nothing but the unit of mutual inductance, which is basically Henry. H is the short symbol of it. Like Newton, you write N, same way, Henry is H. So 1 Henry of mutual inductance is when 1 ampere of current here produces a flux of 1 Weber over here. Then the mutual inductance is said to be 1 Henry. Is this clear, everyone? Awesome. Great. That was mutual inductance. Similarly, imagine a coil like this. The coil itself is carrying some current. That current itself is producing some magnetic field in it. So definitely there is some flux associated with it within itself. So the flux within a coil, due to its own magnetic field by the current, is again called as the flux linkage. is again called as the flux which has been linked, or the flux linkage. And this particular flux obviously is going to be proportional to the current passing through it. More current, more flux. Less current, less flux. Also, it also depends on one more thing, which is the number of turns. I have not shown over here. Obviously, it will depend. More turns, more flux. I into basically N. I into basically N. If you bring that N as a constant of proportionality and also more constants, whichever are there over here, I can write it as equal to, and then there is I, and that constant becomes as L. This is called as self-induction or coefficient of self-induction, self-inductance. Just like before, it again depends on geometry, more turns, radius, shape, etc. depends on geometry. It also depends on the material which is placed inside, and it is again a scalar quantity, and unit is again Henry. Same thing. Unit is again Henry. There is no difference there. So I need to block this. Phi is equal to Li. Till this point, absolutely clear? Everybody with me? Great. Now that you have understood till this point, what might be the self-induction of a solenoid? If you ask me, if I have a solenoid, just imagine like this. This is basically a solenoid. Okay, it is having some length L. Total number of turns is N. So N by L is small n, which is turns per unit length. What might be the self-inductance of a solenoid? How do I calculate it? Because a coil which is carrying current will be a inductor. This is an inductor. Inductor is basically the name given to this particular property of coils affecting each other or itself. That property is called as inductance when it affects itself or others. So how do I find that? Since there is only one coil, I need to somehow find the flux and show it is proportional to the current. Okay. So here is what I will do. The total flux in the solenoid, can I say it is N times the flux through each coil? N times the flux through each coil. N is the number of turns. Each turn will have some flux. So N times of that. What is the flux through each coil? It will be the magnetic field into the area of that particular coil into area of each turn. Correct? That's what it will be. And obviously cos 0, because magnetic field inside any turn of that particular solenoid, magnetic field inside any turn of that particular solenoid is parallel to the area vector of that coil. Area vector of that coil. And this magnetic field inside a solenoid, we know the formula for it. It is nothing but mu naught number of turns into current, number of turns per unit length into current. We have seen this in the magnetism chapter. Oh, so I'll just put mu naught N I over here. This capital N is there, A is there, cos 0 is basically 1. So what I will do is I will write it as mu naught N. Okay, N, can I write it as small n into L? Definitely. Small n into L. This N is as it is, this I is as it is, this area is as it is. Rearranging it further, it will become mu naught N into N is N square, L A into current. Wow, perfect. This is the total flux. Can you see flux is directly proportional to the current? Flux is directly proportional to the current. When flux is proportional to the current, the constant becomes the inductance. Therefore, the self-inductance of a solenoid is mu naught N square length of the solenoid into area. Is this absolutely clear, my dear students, how we found this out? This is self-inductance of a solenoid. Self-inductance of a solenoid. How did we show it? By showing flux is proportional to the current. So whatever is there will be the self-inductance. Clear? Same way, we can go over here and we can find the mutual inductance of two concentric solenoids. Just imagine this. These are basically concentric solenoids. Concentric solenoids. The outer one, for example, I call it as the primary solenoid. That primary solenoid will generate its own magnetic field like this. And that magnetic field which is generated by the outer solenoid, magnetic field generated by our primary solenoid will be mu naught number of turns per unit length into the current passing through it, into basically the current which is passing through the primary coil, mu naught Ni, right? That is the magnetic field which is generated by it. But not all of that magnetic field passes through the inner solenoid. That outer solenoid is big. In that there is a concentric solenoid. Not all of it is associated for flux. If you notice very carefully, only a part of it, only a part of it is passing through the inner solenoid, which is our secondary solenoid. Inner solenoid, which is basically our secondary solenoid. So if you see the flux in the secondary, the total flux, is it not the number of turns of the secondary into the flux through each of the secondary coil? How much is that flux? It will be magnetic field which is passing into the area of that particular secondary coil into cos 0. Field into the area. Area is of this part, only this part, because I don't have to take the total area, only this area, because that is where the flux is passing in that secondary. Okay, so this is N2. What is B1? It is nothing but your mu naught N1, and you have your current which is I1, and this A2 is as it is, cos 0 is 1. So therefore, that total flux will be, observe this carefully, mu naught is there. N2, I can do one thing, N2 by length is basically small n2. So therefore, capital N2 is L times of small n2. So L times of small n2, that is N2. Then mu naught N1 is as it is. Current 1 is as it is. And coming back to A2. So therefore, our flux will become, observe this carefully, mu naught. I have N1, I have N2, I have the length, I also have the area. The only thing which is outside is the current. Flux in the secondary is proportional to the current. Flux is proportional to the current. So whatever is there inside, what will that become? The moment flux is proportional to the current, the inside term will become mutual inductance. So mutual inductance will be mu naught N1, N2, length into area of the secondary coil. Very, very again important formula. This is exactly what they have derived over here also. If you see, no, these same things they have derived here. Mutual inductance, okay, self-inductance of a solenoid, all these things they have just basically derived the same thing. See, mu naught n square. Yeah, same things they have kept it. Okay guys, clear till this point? Mutual inductance formula, self-inductance formula for a solenoid. Okay, clear? Perfect. Now, one more thing which you should know. One more thing which you should know. See, when these things are happening, when the flux in the secondary is mutual inductance into current in the primary. If I differentiate the left hand side and find the EMF in the secondary coil, which is minus d52 by dt, this is as per Faraday and Lenz, then this will become minus derivative of m into that particular current. But m is a constant, so bring it outside. So therefore, the EMF induced in the secondary will be negative m is there, and then you just have the derivative of the current. That's it. This is again an important formula to find the EMF. Just use Faraday's law. Differentiating flux, we get EMF. So EMF in the secondary coil is negative mutual inductance di by dt. Again, something which you should know. Again, something which you should definitely know. Same thing you can even do for the self-inductance, guys. Same thing you can even do for the self-inductance. Observe this now carefully. Because the flux in a coil is directly proportional to the current, the constant of proportionality being L. So the EMF induced in it, which is minus d phi by dt, again this is as per Faraday and Lenz's law. So that EMF will become minus d by dt. We have that current and that self-inductance. L will go outside because it is a constant. So therefore, the EMF will become negative di by dt, and that self-inductance will just be over here. It's the same formula again. Instead of m di by dt, it will become minus L di by dt. Okay, this is the EMF which is generated in that particular coil. You should know one more thing. You should know one more thing though. The energy stored in an inductor carrying current is given by the energy which is stored is given by half inductance into current square. Very important formula. Half Li square is the energy which is stored inside that inductor. It's not difficult to remember it, like energy stored in a capacitor, half CV square. Instead of capacitance you got inductance, instead of voltage you got current. Same but different. Same but different. Hi Mrijesh Arvind, I'm so glad. I hope you enjoy all the classes and be very regular in the days to come. Bunny understood, very good. Yes, half Li square. Just to give you some simple examples so that you understand these formulas. If the current changes in a primary coil at 2 milliamperes per second, where mutual inductance is 0.5 Henry, then find the EMF and current in the secondary coil of 10 ohms? That's the question. There are two coils, that's why mutual inductance. Current is changing at a certain rate, so flux is changing, so electricity is produced. Mutual inductance is given to you, you have to find the EMF and the current. I just now told you, in order to find the EMF which is produced in a mutual case is given by m di by dt. You can see mutual inductance is given, the rate of change of current is given. We just have to find the magnitude of it. So the magnitude of the EMF produced will be m times di by dt. Mutual inductance clearly given as 0.5. Rate of change of current 2 milli. So 2 into 10 to the power minus 3 amperes per second. 2 into 0.5 is just 1. So 10 to the power minus 3 volts, or basically 1 millivolt, is the magnitude of the EMF which is being generated. If you ask me the current, that will be the EMF divided by the resistance of that coil. EMF is 1 millivolt, resistance is 10 ohms, so it will become 0.1 milliampere. That is the current produced. That is basically the current produced. Is that okay? That's how you solve this. Let's take another example. If an inductor stores 10 joules of energy for a current of 0.2 amperes, find the inductance and the flux which has been linked. Find the inductance as well as the flux which has been linked. Let's try to understand it. Because energy is involved, obviously we have to use half Li square formula. Okay, so energy is half Li square. But I don't know L. Maybe that's what we have to find. Okay, is the energy given? Yes, 10 joules. Half is half. L, I don't know. Current, it is already given 0.2. So 0.2 square. So therefore, L will become 10 multiplied by 2 divided by 0.2 square, which is basically 0.2 into 0.2, which is actually 1 by 5 into 1 by 5. Is that right? 0.2 is nothing but 1 by 5. So 0.2 comes below. So 1 by 5 into 1 by 5. 10 2s are 20 into 5 into 5. That's what will happen when it goes on the top. So L will become 20 into 5, 100. Into 5, 500. So it will become 500 Henry. So that's the inductance. Job done. But there is one more question in this. The second part of the question says find the flux. The flux which is linked is L into I. Remember, Phi is Li. L, I already know, it is nothing but 500. Current, I think it was already given to me as 0.2, guys. Okay, so decimal goes inside. It will become 50 into 2. 50 into 2 is 100. So 100 Weber is the answer. 100 Weber is the answer. It's very straightforward questions which are usually asked, so don't break your head too much. Very, very straightforward questions. Cool, guys? Okay, so that is inductors. Now the last part is AC generator, which we'll be talking about. And they have given the construction of the AC generator. And then they tell you how AC generator works, and there is a formula for that. Alternating current. So to show that, best thing to do is use the simulation. Now if you remember, just some time back when we started the discussions, I told you electricity is generated either by magnetic field changing, area changing, or theta changing. Magnetic field changing, we did this problem. where the magnetic field changed to 0 in this much time. Here angle changed, or even the area vector can change. So, this AC generator is actually a problem where you will see the angle between the area vector changes with the time in that field. Notice there is a coil. Notice that there is a beautiful coil over here. This coil has some area associated with it. This coil has some area associated with it. So this might be the area vector of that particular coil. This might be the area vector of that particular coil. Can you see some polarities? That is external bar magnet. Maybe there is a magnet which is placed like this, like a horseshoe magnet. Between those jaws or those clamps, you have a coil which can freely rotate. So definitely there is now a magnetic field which is involved over here. That magnetic field is, over here like this. You can see that very easily. As the coil rotates, you can see with some angular speed, what will happen? The angle between area vector and magnetic field will keep changing. So at any instant, if you measure what is the flux, it will be B A cos theta. But there could be n number of terms, so n. So EMF, which is negative d phi by dt, will become negative derivative of this whole thing, which is B A cos theta into n. But many things are constants, like B is a constant, A is a constant, n is a constant. Only thing which will remain is derivative of cos theta with respect to time. But in circular motion, we have seen omega is the angle covered per unit time. So therefore, theta technically is omega t. So what I can do is, wherever that theta is there, instead of that theta, why not write it as omega into t? Now finding the derivative becomes slightly easy. So minus BAN, cos derivative is nothing but negative sign. So negative sine omega t, and that omega also comes outside. That omega also comes outside by AX plus B rule. Negative negative becomes positive, so it will become BA omega n sine omega t is the EMF generated. All these are constants, so I will write that constant as E naught sine omega t, where E naught is born, BA omega n. If you notice this carefully, you will realize this is a sine function. This is a sine function, guys. You know what it means? It means the EMF will go like a sine wave. Sometimes the current is clockwise, sometimes the current is anti-clockwise. So the direction of the current is sometimes positive, sometimes negative, means sometimes clockwise, sometimes anti-clockwise in the coil. So the current is alternatively changing the direction, hence it is called alternating current, AC current, the one which comes in your house to light up the fans, bulbs and the computers. So this is your AC generator working principle based on Faraday's and Lenz's law. The formula of the EMF is born sine omega t. Sine tells you it will become positive, negative, maximum, minimum, 0, maximum, minimum, alternatively changing the direction. The maximum value is E naught, that is the amplitude of the EMF, which is B A omega n. B is field, A is area of the coil, omega is the angular speed, n is the number of turns of the coil. Let's have a look at it. It's going to be beautiful. Wow, we have a tap. I can turn on the tap and I can see that this will rotate. I can see this bulb will probably light up. Are you ready for AC generator? Okay. Can you see? It is rotating it. Oops. It is rotating it. This is like a turbine. What is happening? This magnet is rotating, because of which in this coil, once the flux is increasing, decreasing. While increasing, the current is in one way, other time it is the other way. And slowly you can see the current is increasing, decreasing. EMF is increasing, decreasing. So that's what is happening. Can you see that? Let me increase the RPM. More water flows. Very quickly, dug, 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 it is rotating. The frequency has increased. I can increase the number of turns or decrease it. If I decrease the number of turns, you can see it very clearly here. The electricity produced is not so much. But if I increase the number of turns, the electricity produced is more, number of turns. Here number of turns is less. If I reduce the area, the light produced is less, electricity is less. Here, if I increase the area, the electricity produced is also more. So it shows it is proportional to area, proportional to the turns, also depends on omega and everything else. Yeah, so this is your AC generator. Such a beautiful, beautiful thing, isn't it? That is what has been exactly explained over here, and they have shown that same graph which I showed you. In fact, there is a problem also on this. I think this is on mutual inductance. Yeah, okay, fine, no problem. Two concentric coils, one of small radius R1 and another of large radius R2, such that R1 is much, much larger, coaxially obtain the mutual inductance. This is like your solenoid, but only one turn. No issues. We'll solve this, not a big deal. So there is a small coil here. R1 is the radius. And then there is a large coil over here. R2 is the radius, R2 is much, much larger. So that large coil might be carrying some current. Okay, let's say it is carrying some current I2. It will produce some magnetic field throughout. So some of the magnetic field lines will definitely pass even over here like this. That magnetic field is given by mu naught current divided by 2 times of the radius. Remember, that's the formula which you have seen in magnetism chapter. So obviously there is some magnetic flux which is associated over here. Obviously there is some magnetic flux which is associated over here. So what is that flux? That flux in the secondary coil. Flux in that secondary coil. It will be magnetic field into the area of that coil. Area of that small coil is pi r1 square. So pi r1 square, I'll keep it here. What is the magnetic field? It is mu naught I2 divided by 2 times of R2. So that is your flux. What I will do, this flux I will write it as, this current I will separate it out, I2. The remaining terms which are there, I'll just keep it as it is, like mu naught pi r1 square by 2 times of R2. Can you see that the flux definitely is proportional to the current? So whatever is over here, that should be your mutual inductance. So mutual inductance is mu naught pi r1 square by 2 R2. That's it. That's the formula. Same thing. Mu naught pi r1 square by 2 R2. Same thing. What we have got over here. Always show the flux is proportional to the current. Your job is done. Whatever is the constant of proportionality becomes your mutual inductance. Becomes your mutual inductance. Okay. So, you know, this chapter is very interesting because I'll just show you the introduction. This thing is there, and it starts with Nikola Tesla. It's a very interesting story. 100 years roughly back, you know, Thomas Edison. What did Thomas Edison do? Put it in the chat box. What did he do? He invented something, right? What did he invent? He invented something. Yes, he invented the bulb. And yes, hello Tanuja. And during those times, they had direct current. Direct current is basically that current which you get from your adapter. Like oops, where is my adapter? It's gone somewhere. It's not there. Anyways, I can't find it. So that adapter, that mobile charger, what you get is basically adapter. It gives you direct current. Even these things, these batteries, what do they give? They give you direct current, right? They give you basically direct current. Yes. Then it was Edison who told, sorry, it was Tesla who told that actually you should not use direct current, you should use alternating current. Alternate means once this, once that, once this, once that, once positive, once negative, once this way, once that way. That is alternating. You keep changing. You should use that. It is better to transmit it easily. It is easy to convert it. It is easy to change the voltages. There are little power losses. Hardly any heat energy is lost. So it is better. But Tesla was like that Pavam guy who is very sincere, who is very dedicated, who is very research oriented. Edison was a business minded person. Edison was a businessman. He had already established his business in direct current. He felt threatened and then he ran a false propaganda 100 years back saying, you know what, AC is bad, you will get shocked, you will get electrocuted, you will die if AC current enters your body. Although it was true, but it was very safe if you pass it safely, if you have insulated wires and you manage it properly, it was actually good. But then because of this false propaganda, what happened? People thought, oh my God, Tesla, he's trying to brainwash us, he's trying to electrocute us. People are thinking that he's some scary guy, and they believed Edison. And Edison, being the businessman, he earned a lot of money during that time because of, direct current. And then after many years, after Nikola Tesla died, then people realized actually what he said was correct. We were fools. And now in our households, everywhere, what is there? Alternating AC current is there everywhere. So sometimes people realize it little bit late. In fact, he dreamt about transformers. He dreamt about many devices in his mind, and the next day onwards he started working on it and it actually worked. So he said that he used to do something called as lucid dreaming, lucid dreams, and he was able to invent so many machines like the motors, the transformers and so much more. So Nikola Tesla, the main guy behind the alternating current, the usage of it and the changing of the voltages, which is the transformer, all of this. So huge massive respect for Tesla. Oh, now the company name is Tesla, but it is not by Nikola Tesla, it's by Elon Musk, so don't get confused. So this is what is basically there in the introduction part. All right, you can see this was 1856 to 1943, that's nearly 100 years back. All right, even he made one coil saying that you can harness the energy from the surroundings. You don't need batteries, you don't need generators, you need not burn coal, you don't need nuclear energy, you don't need hydro energy, you don't need wind energy, you don't need tidal energy. You can harness the energy from the surroundings. But people thought this is going to threaten their business. Then how will I sell coal? Nobody will buy my coal. How will I sell my diesel or petrol? Nobody will buy that. How will I sell anything? So people got threatened, and it is claimed that his lab was burnt down and all his inventions also caught fire and it was destroyed. Okay, so nobody knows how that mechanism worked, how he was able to harness energy for free from the universe and convert it into electricity. Nobody knows till date. But again, conspiracy theories believe that the equipment did not get destroyed, but some secret agency actually captured those devices and stored it somewhere, and only they know how to harness that energy. We don't know what is the truth, but this is just conspiracy. All right. So starting off with alternating voltage applied to a resistor. So first of all, let me give you some examples of AC. So some examples of alternating current, all right. So let me just give you some of them. So imagine something like this: up, down, up, down, up, down. One's positive, one's negative, one's positive, one's negative, one's positive, one negative. Or like this: positive, negative, positive, negative, positive, negative. Or something like this: positive, negative, positive, negative. Or maybe just like this: positive, negative, positive, negative. Now, what does this positive and negative mean? What does this positive and negative mean? Understand. Positive means that in case, let's say for example, you have a circuit. If the current is going one direction, it is considered, let's say, positive. If the current is going like this, and if the current reverses the direction, then it is negative. If the current goes in the other way. So positive, negative over here just stands for the direction. That's all. Okay. So that is why alternating, one's clockwise, one's anti-clockwise, one's clockwise, one anti-clockwise. That is basically called alternating current. A current which reverses the direction. Periodically. It reverses the direction periodically. So if you ask me what is the period, well, it is from here to, it is basically from here to here. This is one time period. You can even go from here to here, one peak to another peak. This is also one time period. From here to here, it is one time period. Or even from here to here, that is also one time period. Even from here to here, that is also one time period. Or from here to here, that is one time period. Is there any relationship between time period frequency and angular frequency? Yes. This F, which is just your frequency, my dear warriors, frequency, F is just 1 by the time period. Not just that, there is another term called as angular frequency. If you have heard this term in SHM, oscillations and so many other places, omega is nothing but 2 pi into F, which is also the same as 2 pi because F is 1 by T, it is 2 pi by time period. The unit of omega is radians per second. The unit of just frequency is just hertz, basically hertz per second. Because time period, the unit will be just seconds. Time is measured in seconds. Frequency is 1 by second, which is a hertz, and angular frequency is 2 pi by T. This is radian, this is second. So radian per second, that is your omega. I hope this is absolutely clear. Another parameter which you should know regarding this is how high it goes and how low it goes, that extent till which it goes up and down on either side, like this. This thing is basically called as the amplitude. This is called as the amplitude. So amplitude is the maximum variation in the current or the voltage. Amplitude. Sometimes also it is called as the peak value, peak or the amplitude. A is how much variation is there from its standard mean average value. And standing here, Shreyas sir is standing here, Shreyas sir goes here and then goes here. Some people have that habit. When they are thinking about something, they will go like this. They are worrying. how much marks will I get in NEET exam? Okay, will I get 700? Will I get 650? Okay, if I study for 5 days, if I study for 4 hours per 5 days, and then I will complete this chapter, and I'm thinking something. So from here, I went 2 meters here, I went 2 meters here, 2, then 2, then 2, then 2. So from my average position, I moved this side 2 meters, this side 2 meters. So my amplitude is 2 meters. So the variation which occurs from the standard average value. Correct. Crystal clear, Atluru, Sneha, very good. Yes, Nicola. Tesla is also in the chat box. Wow, so cool. Very good, Disha. Awesome, awesome. Krishna. Let's move ahead. Now, what happens? Oh, by the way, what is the symbol for alternating current? You should know this. The symbol for an alternating current source, it is like this. This is a symbol of a alternating source. That means, let's say you have a plug point in which you put your plug and current is coming from there, or generator is there which is giving electricity, or some power plant is there. So this is the source of the electricity, but this is alternating source. For DC, remember, it was like this. You put a big line, small line, negative and positive. So this is for DC. For AC, it is one circle with line like this. Who is positive and who is negative here? Can you guys quickly think and tell me who is positive and negative? Smart answer. All the smart kids will answer very quickly now. Which side is positive, which side is negative? Quickly tell me in the chat box. Very good. Yes, nothing is positive, nothing is negative. It keeps changing. Once this is positive, this is negative. Next time this is positive, this is negative. So it keeps alternating. AC, correct. So it is not like one side is positive, one side is negative always. It keeps alternating. It keeps changing. Correcto. Perfecto. Amazingo. Moving ahead. What happens when you connect an alternating circuit to, you can see this is a source, to a resistor? There are some interesting things in this paragraph. I will just probably, mark some important formulas right over here. Let's say this is the voltage difference, this is the current, where I is equal to this. This is one important thing. Let the potential difference be also called as the AC voltage, where Vm is the amplitude of the oscillating potential. Okay, applying the Kirchhoff's rule. Okay, this is what we get, and this is the equation in Ohm's law. Works equally well for both AC and DC. Pure resistance and the current fluid is given by this are plotted. Note in particular, both V and I reach 0, minimum and maximum at the same time. Clearly the voltage and the current are in phase with each other. These are the important lines in this. Let me explain. So when you are attending any of these classes, keep your NCERT also open, because I follow exact NCERT line by line, and you can start marking exactly the same things in your NCERT. Unfortunately, I cannot share this with you because of copyright restrictions, okay, of NCERT, but other than that, you can directly start marking it in your NCERT. Now I will explain this to you. What do I mean by this? That is very important. Let us understand this, guys. See, you have an source, AC source, and then you have a resistor right over here. This is your AC source, and what happens is, now there will be some current which will be flowing in this particular circuit, and also there is some voltage which is generated by this particular source. There is some voltage or EMF which is generated. Either you use the symbol E or you can also use the symbol V. One and the same thing. Don't get scared if somebody uses E. Okay, it is the same as the voltage difference. Let's say I call it V also. Doesn't matter. Okay, now observe. Imagine the source produces a voltage. The source produces a voltage V, which changes with time, and it looks like this: V naught sine omega t. Why this is like this? This is the equation of an oscillating, pulsating, sinusoidal, alternating, whatever name you want to call, voltage. Sine. How does the sine graph look? Positive, negative, like a bumpy ride. speed breaker type. Sine voltage, sine graphs always look like that. So what does this mean? This just means that if somebody decides to draw a graph versus time of the voltage, this particular graph will look something like this: positive, negative, positive, negative, like this. And the maximum value reached will be V0, and here this side will be negative V0. This will be positive cycle, this will be negative cycle. So plus V0 to minus V0, it will keep oscillating, and needless to say, from here to here is basically one time period, which is 2 pi divided by omega. Remember, omega was 2 pi by t. I just gave it to you. Omega was 2 pi by t. So t will be 2 pi divided by the omega. Hence, this is one time period, one crest and one trough, one peak and a valley, one up and one down, one positive and a negative. That is one cycle. So that is time period. That will give you omega, which you substitute here. It looks like the equation of simple harmonic motion, or a sine graph, or basically a wave, or a graph which goes up and down periodically like a sine function. Yes, this is why voltage is V0 sine omega t. This V0 stands for the amplitude of the voltage. Amplitude of the voltage. This over here is the voltage. This is the voltage at any instant. This is the voltage at any instant. That t over here represents that instant of time when you are calculating it. Omega I have already defined and told you before this. Is this clearly understood how this equation is written down? Everyone with me? Okay. Now let us apply Ohm's law. Let us apply Ohm's law. Ohm's law, or basically Kirchhoff's law, whichever you want to apply. Kirchhoff's law, whichever law you apply, my dear warriors. That applied voltage at any instant should be the current, should be the current multiplied by the resistance. Should be the current multiplied by the resistance. Should be the current multiplied by the resistance. Therefore, the current value will be nothing but the voltage divided by the resistance. But wait a minute, I already know what is the value of the voltage. The value of the voltage is V0 sine omega t, and the resistance as it is stays over here. V is nothing but V0 sine omega t. So V0 sine omega t is put here, resistance is staying there as it is. So how about writing this entire equation in a simpler form? I is equal to, this is a constant, this is a constant. Write it as I0. I is equal to nothing but I0, and the same sine omega t I can put it over here, where I0 is maximum amplitude of the current. The amplitude of the current is nothing but your voltage amplitude V0 divided by the resistance. So this I0 is nothing but the current amplitude, the amplitude of the current amplitude, the current amplitude. Is that right, my dear warriors? Understood till this point over here? Very good. All these formulas again they're over here, but it's just that I'm doing this for you so that you see how it is done. Because when a text is presented, sir, what to look, up, down, sir, I didn't understand. You explain it line by line. That's why Shreyas sir is coming over here with a blank screen with the NCERT text, underlining everything for you. Okay, this is the maximum variation in current. Can I plot the current over here? Yes, of course. See, voltage was a sine graph, even the current is a sine graph, meaning the graph of the current will exactly match this one over here. This will also go up and down, up and down, up and down like this. This will be plus I0 and this will be negative I0. That's why current amplitude. I hope you can see that. Now, from this graph, don't you see when this is going up, this is going up, this is going down, this is going down, when this is 0, this is 0, this is minimum, this is minimum. Imagine I am Pandu and besides me there is Champa. Some Champa is there. Pandu goes here, Champa goes here. Pandu goes here, Champa goes here. Okay. Pandu and Champa both go together. Pandu and Champa both go together. Okay. But the extent till which they go is different. When Pandu goes this much, Champa only goes this much. Pandu goes here, Champa goes here. But their amounts are different. That's okay. But they are in the same situation. When they are left side, both are left. Pandu is left, Champa is right. Pandu is left, Champa is also left. Pandu is right, Champa is also right. Pandu is 0, Champa is also 0. So both of them are going together. They are said to be in the same situation. Another word for the word situation is phase. Phase. I am in a very good phase, bad phase. So both the current and the voltages are in the same phase, like constructive. Yes, correct. So I can say that both of them are in the same phase. Same phase. Sometimes the word used for that is a delta phi. This is 0. This delta phi happens to be a term called as the phase difference. The difference in their phases is 0. That's why same phase, or you can also use the word in phase. In phase. This is also okay. Or the word in phase. This is also perfectly okay. Is this clear, my dear students? Understood? Okay. Awesome. Great. So that is what has been mentioned over here. All right. Now, in the next part, they do some calculation for the power. The fact that the average current is 0, however, does not mean the average power is summed as 0, and that there is no displacement of the electrical energy. That is not true. That's what they say. However, this word does not mean, is very important. Average power is 0. That is not true. And no power is dissipated. That is also not true. In fact, what is true is that, as you know, Joule's heating is given by I square R, does depend on I square, which is always positive, whether it is positive or negative, and not on I, very, very important, and not on the value of current. Thus, in Joule's heating and dissipation of electrical energy when AC current passes through a resistor. They have done that calculation over here. One important value which you must know is the value of sine square omega t. Average is half. Okay. Cos to omega t average is 0. Okay. And finally, they get some equations over here and they block it. Okay. Where Vm is this. Okay. And then over here, this household line voltage is a RMS value with a peak voltage of 311 volts. Okay. And same of the DC case. This shows the advantages of introducing a concept of RMS value. In terms of RMS value, the equation of power, etc., is the same as those of the DC case. Okay. And again, they have put over here the current RMS value. And then another important thing which you should better know, it's there in the side footnote over here. Okay. So these are the important things. I have just underlined them. Now I will start explaining this to all of you. Okay. Just imagine that you have a resistor like this, and through that resistor, this particular current is going. This current happens to be I0 sine omega t. It is sometimes positive, sometimes it is also negative. Now, if you ask me what is the power which is lost in this resistor, one might think, sir, if you look at these graphs, if you look at these voltage sine graphs, or even if you look at these graphs over here or here, you will see one thing: how much ever positivity is there, that much negativity is there. How much ever positivity, that much negativity is there. So if you ask me what is the average value, average or mean value, what will the answer be? The answer will be a big fat 0, isn't it? The averages will be 0. Agree or disagree, my dear warriors? Tell me. Because how much ever positive I go, that much negative I go. That means the average will be a big fat 0. Correct. Oh, so sir, the current or the voltage average is 0. So from this, the average value, which is also symbolized like this. Do you remember these triangular brackets? When you put triangular brackets, means average. So if I say marks of a student, and if I put this, means average marks of the students. Correct? If I put height and I put this, average height of the students. So this is average current is obviously 0. But there is a but. What is that but? The but is the average power is not 0. You will be like, sir, why sir? Average current is 0. Why is average power not 0? The reason for that comes from this logic. See, power at any instant is I squared into R. This is the power loss at any instant, I squared R. So think about it, whether the current is positive or whether the current is negative, the square of the current will always be positive. If every time the power is positive or maximum 0, so how can this number ever be negative, which means how can this number's average be 0? Think about it. Even if the current goes like this, energy is lost. Even if the current goes like this, energy is lost. So it's not like if the current goes like this, energy is lost, and the current goes the opposite way, energy is being, taken back. It's not like that. You go like this, it gives out, it goes like this, it takes back. No, it does not give and take. It just gives and gives and gives, and it loses that energy no matter which direction the current goes. Hence, the average is not 0. This can come like a reasoning question. Is that okay, my dear warriors? Is this understood? Oh, clear? Oh, happy Diwali, Pranav. Evening Star, I know you can hear the pataka, the Diwali dhamaka sounds in the background. Thank you so much, Pradeep. Okay. So, what happens is when you want to calculate the average, when you want to calculate the average power loss, this is your average loss of the power, then R is not changing, resistance is constant. So it will be basically you find the average of I square and multiplied by R. Now you might be wondering, sir, how do I find I square's average value? Well, you substitute the value of current. It is basically I naught square into sine square omega t. Okay, this guy's average you have to find. This guy's average you have to find. Instead of I have put I naught sine omega t, but because of that square, I have squared both these things. I naught is a constant. I naught is a constant, so bring it outside. I naught square. What is remaining inside? You are remaining with sine square omega t. You are remaining with only sine square omega t, correct, into R. Now you will be like, sir, what is the average of sine square? This is what they have mentioned in the footnote. Cos 2 omega t's average is this. You have to remember, and sine square omega t's average is half. You have to remember this. Remember this for every problem. Sine square, cos square, remember this. I will write it down for you, what and all you are supposed to remember also. See this clearly. Sine omega t average is the same as the average of cos omega t, which is 0. Whereas if you even take sine 2 omega t or cos 2 omega t average, that is also 0. What is the reason for that? The reason for that is when you draw any of these graphs, when you draw any of this sine or cos omega t graph, sine graph is like this. So how much ever positive, that much negative. How much ever positive, that much negative. If you draw a cos graph, the cos graph goes like this. I mean, I can draw it below over here. The cos graph goes like this. It starts from highest value, goes down like this, it goes like this, goes like this, goes like this. So this is basically one cycle. This is the next cycle. So how much ever positivity is there, that much negativity is there. So average values, sine 2, cos 2, sine omega, sine 3 omega, sine cos 5 omega t, whatever it is, always their average values are 0. Keep that in mind. But the moment you take sine square, the moment you take square of the sine, this will go up. Square of the sine, this will go up. It will be like this. It will be like this. So this is sine square or basically cos square graphs. So that is the reason why you will see the average value of sine square omega t, which is the same as cos square omega t, that is not 0, rather it is half. So the average value is basically somewhere over here. This is basically half. This is what you should know. Is this absolutely clear? Now you will never forget it. It's not difficult to remember. If it is pure sine or pure cos, it is 0. If it is sine square or cos square, it is always positive. It's above the horizontal line. Hence, it is having an average non-zero value, which is half. Clear, oh, Sneha? Very good. So that is the reason why I can just put over here this as I naught square multiplied by half multiplied by r. But I do not like this. I like this average power in a special way. I square r. I don't like this number 2. How about writing it as I naught by root 2 whole square multiplied by r. So now what I can define this as, this value I naught by root 2 is now called RMS, IRMS square. So where I will put over here, where IRMS root mean square is I naught square by, sorry, not I naught square, I naught by root 2. Maximum by root 2. 1 by root 2. Root 2 value is approximately 1.414. If you take 1 by 4.414, you will approximately get 0.707 times of I naught. This is approximate value that you get. Yeah, this is something again you should be aware of. Okay, 0.707 I naught. This is called as RMS, root mean square value. So why did we do this? Why did we do this? Usually power is written as I square R. So if you notice in DC circuits, we use this formula I square R because the current is constant. So now we have got one current which is called IRMS, behaves like a constant current, just like the DC formula, which produces the same power loss in that resistor. Observe this carefully, guys. What do I mean by that? Imagine this. Our current was changing like this, okay? And the maximum value was I naught. What I have got now is an imaginary constant current whose value is IRMS, which is I naught by root 2, which is almost 70%. 0.7 is 70% of I naught. So this IRMS is that constant direct like current, which produces the same power as of the alternating current, So RMS is that constant current which produces the same loss as that of that varying. Something is going up and down, up and down, up and down. You forget that up and down. You give me one constant value which gives the same loss as that up and down current. That is RMS current. Is this clear, my dear students? The definition of root mean square or RMS. Root mean square or RMS. Similarly, you can also say, you can also say that our RMS voltage, root mean square voltage, is nothing but our maximum voltage divided by root 2, which is approximately 0.707, 70% roughly of V naught, approximately. Is this clear? Next important thing, unless mentioned otherwise, keep this in mind, unless mentioned otherwise, all voltages and currents in AC are RMS only. You never give the maximum value. So for an example perspective, when I say household voltage is 220 volts. What is this 220 volts? It is RMS value. Yes, it is already RMS value. So 220 is the maximum voltage by root 2. Therefore, the maximum voltage is root 2 times 220, which is approximately 1.414 times 220, which comes out close to 310 volts. Yes, the maximum voltage which your household circuits get is plus 300 minus 300, plus 300 minus 300. But if you take that constant voltage which produces the same energy equation, that answer will be 220 volts. Got it, everyone? Crystal clear? Clearo? Everyone with me? Alright, if you have forgotten to smash the like button, do that right now for your Vedantu English channel right away. Yes, in case you have forgotten. Cool. Awesomeness. So this is what has been explained in a different way, but I mean, I've made it very, very simple, lucid, easy to understand for you. Otherwise, you will be like, sir, what the hell happens here in NCERT, sir? Maybe you should only write NCERT. I wish I could write NCERT. Okay, a light bulb is rated 100 watt for 220 volts. Find the resistance of the bulb, the peak voltage of the source, and the RMS current through the bulb. Okay. See guys, clearly in this 100 watt, that is basically your average power, 100 watt bulb. When you put a bulb, it is written 2 watt, 5 watt, 100 watt bulb. Voltage. So that 220 volts is basically your RMS voltage. Okay. So if I want to find the maximum voltage, find the resistance of the bulb and etc. Okay. So first of all, if I want to find the maximum voltage, that divided by root 2 is RMS. Therefore, maximum will be root 2 into VRMS, which is 1.414 into 220, which roughly comes out to be as 310 or 311 volts. Okay, 301, 311, that's okay. If you take exact value, comes very close to 311 volts. I had approximated it to 310. Okay, so don't get scared, sir, you wrote 310 here. Why 311 here? If you do more calculations till the third decimal, it will come to 311 volts. It's okay. Approximately we get the answer. All right. So having said this, I got the maximum voltage, the peak voltage of the source. Option B we have done. Okay, what about the other question? It says, can you find the resistance of the bulb? See, power is V square by R, I squared R. You can use any of these formula. So when I use V squared by R, which voltage is this? It's always the RMS voltage. So therefore, the resistance will be V RMS square divided by the power. So RMS voltage is 220. So 220 square divided by the power, which is 100. So this value of resistance comes out to be as 484 ohms, because 22 square is 484. That is the resistance value. Similarly, another question might be, can you find the RMS current? When you use V is IR, then remember, if this is peak, this is also peak. If this is RMS, then even this is also RMS. This is maximum, this is maximum. This is average, this is average. This is RMS, this is average. Same kind should go together. This can't be maximum, this is RMS. That is not allowed. This is average, this is maximum. Not allowed. Average, average. RMS, RMS. Ram, Ram. Sita, Sita. Gita, Gita. Like that it is. Okay. So, RMS voltage is 220. Current RMS not given. We have to find. Resistance 484. Therefore, RMS current will be nothing but 220 divided by 484, which comes out as you can see over there, 0.454. 0.454 amperes. 0.454 amperes. That is your RMS current. Got it, guys? How to solve this particular question? Everybody with me? Very good. Next, representation of voltage and current and etc. in phasor diagram. This is a very important topic. So I'll tell you, see, anything which oscillates, anything which oscillates can be represented in a much better way. I'll tell you what do I mean by that. Everybody knows the earth is round. Nobody believes the earth is flat, right? Over here, hopefully. We know earth is round, like this. Okay? But this is a model of the earth. The earth is very huge. I can't show you the earth. You are staying on the earth. You can see down. You will see the earth. And this is how the earth roughly looks like. But when you have to show any place, any country, any continent, any city, etc., okay, or just the globe itself in the atlas, how does it look like? It is shown like this in the map view, right? So if you open the atlas, let's say I open the atlas. Oops. Yes, atlas over here. Atlas globe. Yes, this is how it looks like. See? Wow, this is how the atlas looks like. This is our, yeah. This is how it looks like. But does that mean that the earth is flat? This is just a representation of whatever is there here on a 2D dimension, right? This is 3D, this is 2D. This is just representing it. You don't have to take it literally. Sir, so can I go from Canada to Russia like this, sir? It is straight line, sir? No, actually, if you see over here, Canada to Russia is not a straight line. It is a curved line. It is an arc. You have to go in an arc. Understand that. Making sense, everyone? Correct? So it is just a representation. Correct. So, same way, any varying quantity, anything which goes up and down, up and down, up and down, can be represented in something called as phasor, which has similar characteristic. Like in the globe, there was Russia. Here also we have Russia. Here we have something, ocean is there, here, there. So same thing is there on that atlas also. Similar identical quantities, but they are shown in a different way. So understand this very, very clearly, my dear students. Oops. If this graph goes like this, Sometimes the graph might go like this. This is like the cos graph, this is like the sine graph. All these graphs are in something called as in the time domain graph, because the horizontal axis is the time. The horizontal axis is the time. Then you have something called as the phasor diagram. Phasor diagram. In a phasor diagram, you have just one reference line. That's it. You just have one reference line. Phasor diagram. You just have something called as the reference line. This is your reference line. This is your reference line. And you show a vector like thing which is called as a phasor. You show a phasor which looks like an arrow, a ray, which keeps rotating with the same speed as that of the oscillation speed, whose length is same as the amplitude, and whose projection gives me this. Meaning, just observe this very carefully. I will show the phasor like this over here. At the start, at the beginning, when the time was 0, the value was 0. If you draw a line like this, it falls over here. After some time, maybe you go here, after some time, and if you just probably draw a dotted line, maybe this is what you get. So this is the value that you get after some time. After some more time, maybe you reach here. And if you draw the shadow or something called as the projection, you reach here. So this is the value after some more time. You wait for some more time again, you will see that you will reach here. And this is the value that you will get after some more time. Again, after some more time, you wait, you will go over here, and the shadow, of course, will go like this till here, and you can see this particular value over here. So you can go even further down like this, not a big deal. You can go down like this also, okay, like this over here, and you will see the downward values as well over here, and then the maximum value down like this over here, like this. See if you are able to visualize, as this rotates, their shadow or their projection means if you draw lines, if light were to fall here, where will it be on this wall or in this diagram? So if light came from here, this point shadow will be over here, so along this line. This point's shadow will be along this dotted green line. So that is the meaning of shadow or the projection. So how much is the component in the y direction, or how much is the projection, or how much is the shadow, or how much it is along this line, I can get it by drawing these lines. So wherever this is shows me the current situation of this graph. If it is here, I've just started. If it is here, it has reached here. If it is here 90 degrees, it has covered, then it has reached the maximum. If it covered 180 degrees, it has completed half the cycle. If it completes 360 degrees, it has come back over here. If it has completed 270 degrees, it has reached the bottom point over here. So that is why this is called as a phasor diagram. Are you able to visualize this now? Same thing I can also do over here. Slightly better diagram I'll have to draw. I'll just try it. Don't worry. Initially, I will be in this situation here, like this. After some time, let's say here, like this, and the graph that I will draw, oops, like this. So initially yellow line, you can see I was here. Then after some time, you can see I was here. After some more time, you can see I was here. After some more time, again you can see I was here. After some more time, you can see I was over here. After some more time, you can see I was again over here. Correct? Again, after some more time, you can see I was over here. Again, after some more time, you can see I was over here, right? And again, after one complete revolution, you can see again I was over here. So this is how it goes up and down as this thing rotates. So a phasor diagram gives me the situation of a oscillating waveform. Gives me a situation or the phase or the situation of the oscillating waveform. Correct? Yes, correct. So now from this, I really understand what exactly is going on. You need something called as the reference. You need something as the reference. And then you have something called as the phasor. This is called as the phasor. A phasor has a length, of the amplitude of the graph. It has the amplitude of the graph as the length. So this becomes your amplitude. It also will rotate with some angular speed. The angular speed of rotation, is the angular frequency of the graph, is the angular frequency of that particular graph. Also, that is, you can say the time period is the same. It makes sense. In 5 seconds, if it completes one revolution, so in 5 seconds it will complete one wave. If it takes 0.2 seconds to complete one entire wave, it will also take 0.2 seconds to complete one revolution over here. So that is what is there in your phasor diagram. Now imagine this. You have a graph, and there are two waveforms in it. Meaning, let's say one is like this, and the other one happens to be, let's say, like this. In these two waveforms, don't you see their phasors will not be at the same place at the same time? Their phasors won't be at the same place at the same time. Like for example, if you show the phasor of this pink one, initially it was showing 0 value. That means maybe the phasor might be like this, sleeping, because their shadow will fall here. But initially the blue graph's phasor already shows some value. So maybe it was over here already, because you can clearly see certain value over here initially. Whereas for that pink graph, that is not the case. So what is there now between both of them? Over here in this diagram? That is delta phi, which is nothing but the phase difference. Between them. Both of them will be rotating with the same angular speed. Yes, they will be rotating with the same angular speed, but they will maintain their difference between their phases. I hope this is clear. So now going back a little bit in time and going back to this particular thing, if somebody had to draw the phasor diagram over here, will I not show the voltage and the current phasor together always? Will I not show the voltage and the current phasor together? Check this out. Yes or no, my dear warriors? Check this out. So the length of the current phasor will be I naught. The length of the voltage phasor will be V naught. They will always rotate together. They will always rotate together with the same angular speed. That's why they were in phase or same phase or no phase difference. Is everybody clear till this point? Happy Diwali, Kadir. Clear, Sneha? Very good, Atluru. Okay, awesome. So that is the concept of phase difference and this phasor diagram. All right. So now let's go to alternating current with inductor and capacitor. Then we'll combine all three of them and then see resonance, impedance and all of that. So that's almost like the most of the chapter, and then the last concept comes as transformers. So when you take an inductor and then try to solve the question, then what happens to the graphs, etc.? Let's have a look at it. Let's have a look at it. Say for example, this is our source, this is our inductor, like this, L, all right. And let's say the current which is flowing in this case, the current is already known to me as I naught sine omega t, which means if I were to draw a graph, this is time for the current, because it is a sine graph, it will start from 0, reach maximum, reach minimum, reach 0, reach maximum, 0, minimum, and this will continue. This is how it will go for the current graph. If you ask me how the current phasor will look like, it is very obvious from here. It is very obvious from here that the current phasor, I don't know if I have so much space, but still I will use my liberties. And I will show the current over here like this. This is how the current phasor will be. It is at 0. So this is my current phasor, I naught. This is my phasor diagram. This is my phasor diagram. Okay. Now let's try to find out the voltage in this case. Again, using Ohm's law or whatever. So again, let's use Ohm or Kirchhoff law. What do I get is this particular voltage which is there will be nothing but the current into resistance is what you will say. No, there is no resistance here. This voltage will be nothing but the voltage across the inductor. Whatever voltage is there here is also the voltage across the inductor. And I think I know what is the voltage across the inductor. It is nothing but L times negative di by dt, if you remember this from the chapter of electromagnetic induction. Voltage across the inductor is L di by dt with a negative sign. Correct? Oh, so can I differentiate this? Why not? So derivative of the current, which is I naught sine omega t, and L stays over here with that negative sign as it is. So what do I get? What do I get over here? I will get minus L. This I naught will come outside as it is. Derivative of sine is cos omega t. Don't forget, even omega's derivative will come. So it will look something like this. This is how the voltage will look like. Minus L I naught omega cos omega t. Okay, fair enough. Fine, sir. I am interested mainly in the magnitude. So even if that negative sign is there, I am not so bothered about it. Let's not get there. So if you just look at it magnitude wise or whatever, it's forgetting this negative sign. It is exactly this much. Now, usually I write voltage as current into resistance. So I will try to rephrase this entire equation like this. Voltage is equal to current into resistance. So my current is, let's say, I naught. Resistance is this whole thing, which is omega into L. And there is a variable term which I'm okay with, which is nothing but cos omega t. That is a variable thing. Okay, that's fine. Forget this for now. This is variable. Voltage is current into resistance usually. So current is I naught, voltage is V. Won't this term act like the resistance? Omega into L is looking to me like the resistance if I compare it with V is equal to IR. Forget this cos. So actually speaking, this term over here is like the resistance, but there was no resistance. So what do? It's like a substitute for resistance, but it is not actually, you know, the resistance. If you have played some cricket, football, etc., sometimes it happens. One player gets injured. Maybe that person was the fielder. So have you seen this or have you done this? You call one small guy, some junior, hey, listen, camera over here, stand over here. What I have to do? You just come stand here. If the ball comes, just catch it and give it to me. You don't do anything. Just chumma, that person is like one, you know, dummy person. I think you too would have been some dummy like that, or you would have asked somebody, just stand over here. Just stand and just catch the ball and give it to me. That's all. You don't do anything, or just call me if something happens. So same way, this is acting like one resistor. It's like an imposter, but it is not a resistor. So it is not a resistance, but it is like a resistance. So we cannot call it resistance. So that's why we call it reactance. The symbol for that is X because it is of an inductor, XL, L stands for inductor. So this is basically inductive reactance. Inductive reactance. This inductive reactance is omega into L. This inductive reactance is omega into L. So this is anyways cos omega t. Okay, I'm just interested in the magnitudes only, nothing else. So this is your I naught. So you can see this right over here, correct? So if I had to put V naught, V naught will be nothing but I naught. Maximum voltage will be I naught into XL. V is IR. What is V naught? V naught is this whole thing. This whole thing is nothing but V naught, which is the max voltage. V naught cos omega t. Right. So we got it in the Ohm's law form. And we can clearly see that the voltage is a cos graph. Voltage is basically a cos graph, but with a negative sign. Usually cos graph starts from here, but because of this negative sign, I can just say it is probably, you know, starting from the negative value over here, right? So that's all, guys. I can just say it is going like this, reaching like this, reaching like this, reaching like this, and so on and so forth. So that is how the voltage graph will basically look like. But this is considering the sign, but usually we are not interested in that sign, we are interested in that magnitude. So hence you will see, actually speaking, the voltage graph will look something like this. Will look like this. So now, is there a phase difference between them? Is there a phase difference between them? Tell me, my dear students. Is there a phase difference between them? Yes or no? Quickly think and tell me. Is there a phase difference between them? Yes, there is. Yes, there is. In fact, if you show the phasor of the voltage, the phasor of the voltage will be like this. This will be the phasor of the voltage. And you can see there is an angle between them. And yes, both of them are rotating like this with omega. So there is a phase difference, delta phi of 90 degrees or pi by 2 radian. And who is ahead of whom? That is very important. The voltage leads. Very, very important. The voltage leads by 90 degrees to the current. That is very, very important. Is this absolutely clear, my dear students? Yep. If somebody tries to calculate this quantity called as power, and you calculate the average power, believe me, the answer will be a big fat 0. Yeah, the answer will be a big fat 0. So there is no loss due to inductor. In fact, inductor acts like a storing device. If you remember, energy is always stored in an inductor, half Li square. It never loses energy. So an inductor never loses energy. Resistor will lose energy. That is what has been explained in all these questions and all these, equations over here. Okay. So this is what you should know regarding an inductor. I have made a beautiful slide for all of you. All right. So having said this, is there a question on this? Yes, there is a small question on this. You can see it right over here. Let's try to have a look. There is an inductor of 25 millihenry. Yes, the Henry is the unit of inductance, to a source of 220. Find the reactance RMS current in the circuit if the frequency is 50 Hertz. Frequency is 50. Omega will be 2 pi f, which is 2 pi multiplied by 50, which is 100 pi radian per second. That is first of all given information. Inductance 25 into 10 to the power minus 3 Henry. RMS value of the voltage is given to be 220 volts. Okay. All these are given information. First, can we find the inductive reactance of the circuit? XL. What is the formula? XL is omega L. XL is omega L. Omega is 100 pi. Inductance 25 10 to the power minus 3. So 2 zeros goes, this 10 goes, so it will be 25 pi into 10 to the power minus 1 ohms. So this 25 pi, if you multiply it, it comes out to be 7.85 ohms after taking this decimal also into account. So that is the inductive reactance. Yes, please remember the unit is ohms only. So the unit of this is a ohm. It is not anything else. It is like a resistance. It behaves like one. So the unit also is the same thing. So that is the answer. If you ask me the current in the circuit, the RMS current is voltage divided by resistance. But I don't have a resistance. So what I will do? I will take inductor's reactance. So RMS value was 220. Reactance was 7.85. So when you divide both of them, what do you get? Approximately 28 ampere. So that is your RMS value. Is that clear, my dear warriors? Very good. Now, moving ahead to the next concept is of the capacitor. Same thing you do it for the capacitor also. Same thing has to be done for the capacitor. So the next topic, 7.5, is a source with a capacitor, and then they have done the same analysis over here. So my dear students, if you take a AC circuit with a capacitor like this, since it is alternating, current will go once like this, once like this. Okay. And this will be the voltage. Let us say our voltage is V0 sine omega t, which means on the time domain graph, our voltage will look like this. This would be V0. So we all know that for the capacitor, the charge at any instant, the charge on it at any instant, let's say there is some plus Q charge over here, and some minus q charge over here. That charge will be nothing but the capacitance multiplied by the voltage. But the voltage itself is V0 sine omega t. Okay, so I'll put capacitance over here, and this is basically your charge. Now what I will do, I can find the current, which is nothing but dq by dt. So take the derivative of this. In this derivative, the capacitance is a constant, even the voltage amplitude is a constant. So the only derivative will be of the sine omega t term. Only derivative will be of the sine omega t term. What is the derivative of sine omega t? Let's find out. Therefore, the current will be, you have your capacitance as it is, you also have your voltage amplitude as it is. Derivative of sine is cos omega t, and that omega will come outside. This is what you will get. This is what you will get. But I don't like this form, so I will write it in a slightly more beautiful form, where current is voltage into resistance. Where current is voltage into resistance. Voltage by resistance, my bad. Current is voltage by resistance. So this is voltage, which is V0. That cos omega t is a varying term, so let's just forget about it. It's just a variable term, that's okay. C and omega are on the top. Current is voltage by resistance. So deliberately I will do one thing. I will divide this by 1 by omega c. Because if you take it on the top, omega and c will come over here in the numerator. Why did I do it deliberately? Current is voltage by resistance. This looks like resistance to me. So now my current will be voltage by an imposter of resistance, not a real resistance, but like a resistance. This is due to a capacitor. So an imposter like that is called reactance X, but due to capacitance, so C. And then you have that cos omega t, where your capacitive reactance, again the unit of that is ohm only. This XC is 1 by omega c. And you can also notice one more important thing. This whole thing over here, what you see, right? This whole thing over here, what you see is actually I0, some constant into cos omega t. So I0 technically is maximum voltage by the resistance imposter, which is capacitive reactance, just like the Ohm's law. Is this absolutely clear, my dear students? Okay, very good. So now, if you were to draw a phasor diagram, this is the reference line. My voltage phasor would be like this over here. My voltage phasor would be like this over here, which is a sine graph. The current graph is a cosine graph. The current graph is basically a cosine graph. So this will start like this. Oops. The current graph is a cosine graph, which will start like this. This is I0. Here current is a cosine graph. Here earlier you saw the voltage was the cosine graph. So you will notice that the current's phasor diagram will be over here. This is your current phasor. You can see there is some angle between them, 90 degrees. Yes, both of them are still rotating with the same speed. They maintain their phase difference. In this case, obviously, the phase difference again is 90 degrees or pi by 2 radian. But here I will say it's the current which is ahead of the voltage. So the current leads whom? The voltage leads the voltage by 90 degrees. Current is ahead of the voltage by 90 degrees. Earlier, it was the voltage which led the current by 90 degrees. So this is again very important. If somebody decides to calculate the average power, it will be 0. There is no power loss because capacitor again has the ability to store the energy. It will not cause any losses. So the power loss, just like inductor had no power loss, so here also the power loss will be a big fat 0. Alright, so let's have a look at a question maybe. There are some questions over here. There is some capacitor, some frequency, find the reactance, RMS current, etc. If the frequency is doubled, what happens to the reactance and the current? Okay, simple guys. If frequency is given, omega is 2 pi f, 2 pi into 50, which is 100 pi radian per second. Talking about reactance, capacitive, is 1 by omega c. So 1 by omega is 100 pi. Capacitance 15 micro. 15, 10 to the power minus 6. When you do the math, they have found out the answer. It comes out as 212, but this is in ohms. Then they have also asked what is the current in the circuit. In order to find the current, you will take the voltage and divide it by the resistance like thing, which is reactance over here. The voltage is 220 in RMS. Reactance, we just figured it out to be 212. This approximately has come out to them as 1.04, almost very similar, 1.04 amperes. That is the answer to the first part. Correct? Second part, what will happen to the frequency if it is doubled? Think about it. If frequency is doubled, then even omega will be doubled and it will be nothing but 200 pi radians per second. So because of which your xc, the new xc, omega is below, so it will be the old x divided by 2. Whatever was there, it will be divided by 2 because omega has been doubled. Numerator has not been changed, denominator has expanded, so the ratio will decrease. So you will see that the reactance will become half of the previous one. So it will be nothing but 106 ohms. 212 will become 106. If you ask me what will happen to the current, well, current is Vrms by XC. Resistance has decreased by 2 or half a factor. So RMS will increase, RMS current will increase 2 times. If resistance reduces, current increases, more current will flow. So whatever was the old current, it will basically increase. So it will become 2.08 amperes. Yes. Yeah. They have also asked what is the peak. You can easily calculate it. If this is RMS, peak will be nothing but, if the peak current was asked, it will be √2 times 1.04. They have calculated it to be 1.47 amperes. If the maximum value was asked, that also you can do. Oh, thank you for reminding me for having water. I thought of giving you guys a break also now. I'll just give you guys a break. This was last example before we take a break and then we'll again return. A light bulb and an open coil inductor are connected to an AC source through a key as shown. In the figure, the switch is closed after some time and iron rod is inserted in the interior of the inductor. The glow of the light bulb will increase, decrease, unchanged as the iron rod is inserted. Okay, so when you have an inductor and let's say you have inserted some iron rod inside of that, what happens to the inductance? Can you guys quickly tell me what happens to the inductance? Yes, the inductance increases. Why? Because that rod is iron, which is ferromagnetic material. So mu, magnetic permeability will increase, more field lines will be there. So inductance will increase. It is ferro. Instead, if it was a diamagnetic material, no, then it would have decreased. Para will increase, ferro will increase, dia will decrease, die, go down, paragliding, go up, ferro, even better, you increase even more. So that's why it will increase, and because of that, what will happen to the XL value? XL is omega L, that will also increase. Because of that, what will happen to the current, my dear warriors? Current is voltage by XL. If this goes up, this will go down. So the current decreases. So current will decrease. That means the power of that bulb which is there, which is I squared R, that will decrease. Hence, the brightness will also decrease. That is the answer. Hence, the light bulb brightness will decrease. That is a very interesting thing. Many people think it would have increased. But if the question said not iron rod, diamagnetic rod, then everything will be opposite. Permeability will decrease, L will decrease, XL decrease. So current increases, power increases, brightness increases. So a diamagnetic rod will increase it, para and ferro will decrease the brightness. Is this clear? Very good. So we will do this and resonance and transformers after a short break. It is not that difficult, but we will take a break. Meanwhile, please like the video in case you have not liked it. Like the video and also subscribe. Subscribe to the channel in case you have not done that. Okay, we'll just return in a bit.
Hello. Yes, am I audible? Hi, Krishna, Nicholas, Latluru. Welcome back, welcome back, welcome back. And my AC also has stopped working now. Oh my god. So it's time to remove this. Okay. So, welcome back, my dear students. It's time to talk about LCR circuits together. Before the break, we have seen that when you pass an alternating current through the resistor, the voltage and the current are in the same sync. They are in the phase, no phase difference. But the same thing if you do it for an inductor, you will see that the voltage and the currents are not together. In fact, there is a difference of 90 degrees. The voltage is ahead of the current by 90 degrees. Yes. And in the case of a capacitor, it is the current which is ahead of the voltage by 90 degrees. They are not in sync. And there is an imposter to the resistance, which we call as the reactance. For the capacitor, it is 1 by omega C, and current is voltage by that reactance for the capacitor. So naturally, same thing for the inductor also. There is inductive reactance omega L, and voltage is current into the resistance. Right? That is what you have seen. Hi Ruthlessness, hi Mardai. Good evening, Sneha. Good afternoon, everyone. Welcome back. Yep, all our regular students are back. So time to see LCR circuits and what have they explained in these three slides over here. See, the first slide they have talked about the basic circuit and how the voltages etc. will be written down in equation using Kirchhoff's law. The next slide they have done the calculations part of it, and they have introduced a term called as impedance. And finally, they have drawn the phasor diagram and calculated the phase difference in general for the LCR circuit. Okay, so let's understand this. So you have an inductor, a capacitor, and a resistor, LCR circuit, which is connected to a AC source like this. What will be same in all of them? What will be same in all of them versus what will be different is the voltage will be different, but the current will be the same. Whatever current will come, the same current will have to flow through the circuit. So the current will be the same. So I naught sine omega t will be same in all of them. So let's say over here, this is your time, this is 0. So the current graph is like a pure sine graph like this. Okay, this is your current graph. All right, I naught. If you talk about the phasor of the current, let's say it is like this. This is basically your I naught. This is the current phasor. Now, if you apply Kirchhoff's law, if you apply Kirchhoff loop law, you will see as you pass across the circuit, the voltage of the AC source, then over here, first drop you get voltage across the inductor, next drop voltage across the capacitor, minus voltage across the resistor. Finally, you will get this as 0. So if you move this on the other side, you will get the total voltage of the AC source is voltage across the inductor plus voltage across the capacitor plus voltage across the resistor. Now, voltage across the inductor is L times di by dt, right? Capacitor's voltage, Q is CV, so V is Q by C. That means it will be Q divided by capacitance over here. And across the resistor, it is just I into R. So this is what the equation will look like. Now we don't deal with the mathematics part of it. Don't worry about that mathematics, how to solve this equation, but this is how the equation will look like in case they ask you in your board exams, or maybe as an option in your NEET or any other competitive exam, right? So after this, when you solve this equation mathematically and get the final answer, that is what is more important to us. We get this voltage across AC, which we call it now as V. This voltage and this current, they are related as follows. They are related as follows. This voltage will be nothing but the current I naught into root of R square plus XL minus, or if you want I can write omega L minus 1 by omega C, this thing square, and here you get cos, or sorry, sine, whatever, because this was sine, so sine omega t plus, my goodness, sine omega t plus some delta phi. This is the solution that you get, and you will be wondering, sir, it is such a scary equation, but actually it is not. I will tell you why also in a bit. I'll explain everything one by one. If you just concentrate on this entire term, this is a constant term. This is some sine cos function. It's varying up and down. Forget that. This is that constant. So this is V is equal to something sine or cos. This something should be the amplitude. So this is your voltage amplitude. So this is nothing but your voltage amplitude. Voltage amplitude of that AC source. So that is basically V naught, and this V naught is nothing but the current multiplied by that entire thing which you got over here, R square plus omega L minus 1 by omega C whole square. Now you might be wondering, what is this actually called? Is there a name for it? The answer is yes. This term is like resistance, but it is not resistance. V is IR. So all this thing in yellow is like resistance, but it is not resistance. It's a combination of resistance. Do you see what omega L is? And 1 by omega C is? They are reactances. So combination of resistance and reactance is then called as impedance. So our impedance is a combination, impedance Z is a combination of resistance and reactance. So it is R square plus, this one was XL, this one was XC, so XL minus XC square. This is what impedance is, and it is also expressed in ohms only. So V is IR is coming many times. You can write voltage is current into resistance, voltage is current into capacitive reactance, voltage is current into inductive reactance, voltage is total current into the total resistance, which is called as impedance. Everything will work. Z is the impedance. Yes. Now, if you have understood it till here, let me go to the next slide and explain to you. Actually, I have already created that next slide over here. Where do these impedances, voltages exactly come on the phasor diagram? That is very important. And what happened to the delta phi, sir? You didn't explain that. Hold on, I'm coming to that also. So first of all, if VL is the voltage across the inductor, VC is the voltage across the capacitor, VR is the voltage across the resistor. This V came out to be V naught sine omega t plus this delta phi. So if you start plotting the voltages on this phasor diagram, number one, inductor's voltage always leads the current. So the voltage across the inductor, I will show it like this. This is voltage across the inductor. Across the capacitor, the current is ahead of the voltage, or the voltage is behind the current. So the voltage across the capacitor, I will show it like this. It's behind the current. Remember, the entire phasor diagram was rotating like this with some angular speed. For the resistor, the voltage and the current are in the same phase, so might as well put it like this. So this is how I will put the voltage across the resistor. Don't you see they are like vectors now? One vector is here, one vector is here, one vector is here. You have to find the resultant of these three vectors to get our total voltage V0. To get our total voltage V0. If you notice very clearly, you will understand. I can actually draw a triangle like this with the base as VR, and VL and VC are opposite. If you deal with these two vectors first, one vector is here, one vector is here. The resultant of VL and VC, will be only this much, which is probably which is only this much, which is basically VL minus VC. I don't know who is big, who is small, so I'll put a modulus. Maybe VC is more, then this diagram will come down below over here. So then what I will see is the resultant of them is basically going to be V0. The resultant of them is going to be V0, yes, and this was 90 degree, of course, because this was 90 degree, yes, and this was also 90 degree. We have seen this before as well, correct? So this is how the vector addition of VR, VL and VC gives me V0. So technically speaking, this V0 vector is VL vector plus VC vector plus VR vector as vector addition. So basically phasors are added like vectors. Phasors are added like vectors. That is the advantage of treating them like phasors. That's the advantage of introducing that particular concept. So from this, if somebody asks you what is the magnitude of V0, you will use Pythagoras and immediately say it is nothing but nothing but this square, which is VR square plus VL minus VC whole square. You will immediately tell this square plus this square is this square. This is using your Pythagoras theorem. Individually, if you ask me this VL, VC, etc., I will tell, also keep in mind, on the next slide, maybe I can do this. Also, I can say this VR, VL, VC and this V0, all of them can be written down as, because the current is same, I can put I naught over here, I naught over here, I naught over here, I naught over here. For resistor, it will be R, V is IR. For inductor, it will be I into XL. For capacitor, I into XC. For total, it will be into Z. For total thing, it will be into Z. Similar looking formulas. V is I into Z. Same thing I have just written down here. These three things we had just seen before the break. Very, very identical looking equations. And since we have also told the total voltage is this square plus this minus this square, and before this also had told Z is R square plus XL minus XC square, this looks very, very similar to me. Impedance is resistance square plus XL minus XC whole square under the root. Same thing, total voltage is resistance voltage plus difference of the voltage across inductor and capacitor square, whole thing under the root. Meaning, instead of VR, VC and all these things, imagine I had drawn a phasor diagram. Imagine I had drawn a phasor diagram of resistors then also I would get the same thing, my dear warriors. So I could have just said, listen, this is basically your current, and I will show VR. Oops. Okay, anyways, I think I made a mistake over here. I should not have erased this slide. My bad. I should have done it on this slide. Yeah. Just 1 second. So instead of the phasors drawn for the voltage, I could have also drawn it for the resistances like this. So this is basically your I naught, and along the current you will have the resistance in the same phase. You will have inductive reactance leading by 90 degrees to the current, and you will have capacitive reactance lagging. It is behind the current by 90 degrees. So this is XC. And if you take the vector sum of all of them, if you basically take the vector sum of all of them, so this was your resistance. This is XL minus XC. I don't know who is big, so I'll put a mod symbol. The resultant over here, this is basically your Z. This is basically your Z. Is this clear? So the same triangles can be also applicable for voltages or even for resistances and impedances. It is one and the same thing. It makes your job very, very easy. Keep this in mind. Now talking about the phase difference, which we were writing over here. Sir, what about this delta phi? This delta phi is exactly over here. So this angle that you see, my dear warriors, this is your delta phi. And clearly you can see, if you take the tan of this delta phi opposite by adjacent, it is XL minus XC, whichever is big, whole thing by resistance. Or here also you can do the same thing. This same angle is there over here also. This is your delta phi. So tan of that phase difference between voltage and the current is nothing but again VL minus VC. I don't know who is big, so mod divided by your VR. This will also do. So this is how you calculate the phase difference between the voltage and the current. Remember, the current phasor will be over here. This is where your current phasor will be. Is this clear? These equations look very similar if you treat them like vectors. Main thing is this only. Voltages are added like vectors, even impedance is added like vector only. Think about it. So Z vector is actually R vector plus XL vector plus XC vector. But if you just look at the magnitude, it is this square plus this square. So R square plus XL minus XC whole square. So even it works for resistances, even it works for voltages. Current is common, so there is no equation like that for current. Current is the same because they are in series, one after the other. Clear? Very good. Now, if you ask me what is the power in this circuit, well. So many things I have to. Instead of that, I will draw only a new thing. That will be better. So when you have a LCR circuit, this was the voltage and this was the current phasor, this was the voltage phasor, this was V naught, this was I naught, and there was some angle between them, delta phi. If you now calculate the power loss in a LCR circuit, it will be the power loss in inductor plus power loss in the capacitor plus power lost in the resistor. If you remember carefully, I have discussed this. Inductor, there is no loss. Capacitor also there is no loss. It's only the resistor where there are losses, and that is I RMS square into resistance. If you remember this carefully. Correct. So it is only across the resistor where the power losses happen. And you can do one thing. You can write I RMS square as I RMS into I RMS into R, and I RMS is actually I RMS is equal to V RMS divided by impedance. So that is what it is. I is voltage by resistance, but this is the total current. So total voltage by the total resistance, which is the impedance. Now I will just rewrite this slightly. So I will put VRMS over here, IRMS as it is, and then I will write R by Z over here. What is the reason for that? So this is the average power loss in your LCR circuit will come out to be the RMS voltage into the RMS current. What is this R by Z, you might ask? Go behind a little bit, see this triangle and tell me what is R by Z. What is R by Z? Adjacent by hypotenuse for this angle. So it is cos. Yes, it is the cos. So it is cos of delta phi. Correct. It is just the cos of delta phi. This cos of delta phi, whole thing is called as the power factor. It is called as the power factor. Very, very important. What is it called? It is called as the power factor. So you have two formulas now. You can write power as I squared R. So this is one formula. Or, so this was either I RMS square multiplied by the resistance, either this multiplied by the resistance, or you can use VI cos phi, but both of them should be RMS only, otherwise it will not work. So very, very important formula. Now, remember one thing. For a LCR circuit, if I draw a triangle like this, where this is VRMS, this is IRMS, and this is your phase difference, which is delta phi. So this is 90 degree, of course. This side is adjacent to the hypotenuse. So this is cos delta phi of VRMS into your IRMS. Same thing if you do it over here. This is opposite to the angle. So this is VRMS into IRMS, but into sine of del phi. If I make an imaginary triangle, this over here is the actual power loss, actual or real power. I hope you guys agree with that. This is the actual power which is being lost. This one over here is basically for a person who does not even understand that, hey, listen, there is something called as phase difference. So that person who does not understand AC will calculate this as the power without noting the power, without noting the phase difference. So that is called as apparent power. That is called as apparent power. This is called as apparent power without considering the cos of the angle between them. So the phase difference needs to be considered, or else you will get the wrong answer. So this is apparent. This is what you feel. This is what you think it is, but it is not real. It is actually this. This side over here, which you see, this one is called as reactive power. Reactive power. So very, very important. This power is basically the one which is oscillating between inductor and capacitor. Remember, inductor and capacitor cannot actually lose any energy. They can only store the energy. So when the inductor has stored the energy, capacitor does not have anything. Then the inductor gives that energy to the capacitor. They keep playing catch. Inductor will throw the energy, capacitor will take it. Capacitor will throw it, inductor will take it. They keep oscillating that energy between themselves. So that is why it is called reactive. Reactive elements means inductor and capacitor. Reactive. Reactance. Yes. So it is oscillating between the inductor and the capacitor. It is not lost. It is just trapped between them, but it is not lost. It is not lost forever as heat. This is the one which is lost as heat, which is, usually consumed, usually lost as heat. This one is not lost as heat. This whole diagram is basically called as the power triangle. Sometimes they might ask you the question, what is the apparent power? What is the reactive power? What is the real power? What is the ratio of both of them? Anything such question might come on this. Clear? Very, very important. So all these things again are there in this whole thing over here. Now, there is a term called as a resonance. We will talk about it and then there are some questions on that. Okay. Now, you have your LCR circuit like this. You have a fixed voltage V0, maximum voltage, and then there is some current which is going over here. That current is I0 sine omega t. Okay. Now, imagine I calculate the current, maximum current which goes, which is nothing but V0 by your Z, but this Z itself has a value which is root of R square plus XL minus XC whole square. Just 1 second, guys. My dear students, I will be teaching in little bit of dark mode over here because what has happened is the lights are, UPS is blinking a little bit, so I might be using a little bit of dark mode. I can't turn on the lights. Electricity has gone, AC is not working, so I don't know how I will look, but it's okay. I don't know, it looks very weird right now, but I can't help it because I want to complete this topic. I don't want to leave this topic. Just 1 second. Okay. Fine. Okay. So I don't know whether you can see my hand or anything. Let's see if I can change some brightness setting over here. Okay, it's slightly better. I think I just changed some camera setting, that's all. So I might look little bit weird, but that's okay. Okay, so basically we were just talking about this is how the current will change with this resistances. Now remember, XL is actually omega L and this XC is nothing but 1 by omega C. That is what we know. Is that right? That is what we know. Okay, perfect. Now, if I change omega, this will change, Z will change, current will change. So if you plot a graph now, this is very interesting. If you plot a graph like this of the current which you get versus the angular frequency, how will that graph look like? That graph looks something like this. It is less initially, it goes up and then it again comes down. That is how the graph looks like basically. Wow, suddenly I don't know why I'm liking this dark mode. The screen looks so much nice and bright. At least I can see the screen over here. It is looking so cool. I'm not sure how it is on your side. Anyways, coming back over here, this is reaching some maximum value, like you can see. It is going up and then it is coming down over here. It is definitely reaching some maximum value, definitely. So if you see where it is maximum, like right over here, this is where the current I0 is maximum value. This happens at a very special value when both XL and XC are equal. Yes, I0 maximum occurs. If you want this current to be maximum, Z should be minimum, and Z is minimum when both of them are equal. That means they cancel out, it becomes 0. So there is nothing to add when this becomes whole as a 0. So basically you will see XL minus XC is 0 or XL is equal to XC. So in general, I can say the value of Z is minimum. The value of Z is minimum and it comes out as R because XL minus XC is 0. 0 square is 0. R square's root is R. So Z becomes equal to R. XL value is omega L. XC value is omega C 1 by. So basically omega square is 1 by LC or omega is 1 over root LC. So this happens at a special value of 1 over root LC. That's when the current is maximum. This entire phenomena is basically called as resonance, or it has been tuned perfectly. It has been tuned perfectly. That is what it is. So your devices around you should always be in resonance condition so that they function and deliver power properly, because that is the situation when current is drawn properly in that circuit. You have a washing machine, you have a TV. If the graph has not reached here, that means the device is not tuned properly, it is not resonating, it is not matching properly. So you have to add some resistor, capacitor or inductor so that it gets tuned and it behaves in sync with the AC source. And that's when it will draw very good power inside the circuit. And at resonance, you will see one more interesting thing which will happen. And because XL is equal to XC, think about it. XL phasor and XC phasor both are opposite to each other. Wow. XL and XC phasor both are opposite to each other. This was your current, by the way. This is how your current will be. So basically they both get cancelled. They cancel each other. And because they cancel each other, you will see Z equals to the resistance. They have to cancel each other. So you will notice that in such a scenario, the voltage will be in the same phase because they both will cancel. Voltage will be in the same phase as that of the current, and you will see in such a resonating condition, the phase difference which you get is going to be 0. The power factor is going to be 1. This will be maximum power condition. Maximum power condition. Delta phi is 0, that means it is in phase. It is in phase. The voltage and the current are going to be in the phase. All these things happen together. Is this clear, everyone? Cool. So this is the condition of resonance which has been given over here also. You can see the same graph has been given. 1 by root LC is given, and yeah, everything else is as it is. So the power loss, or the power which is going to be consumed, which will be maximum, will be nothing but Vrms square, will be nothing but your whatever this voltage is, V naught. So Vrms, you calculate Vrms square divided by R only, because R will be equal to your Z. R will be equal to your Z. Keep that in mind. Okay. So all these things are regarding your property of resonance. Regarding your property of resonance. Keep this in mind. Okay. Perfect. Clear. Let's do some questions then, maybe which are there in your NCERT. Very, very direct questions are there. Like, see, a resistor is given, capacitor is given, they are in series, no inductor is there. Calculate the current, calculate the voltage across the resistor and the capacitor. Is the sum of the voltages more than the voltage? If yes, resolve the paradox. That's okay. All right. So resistance is given 200. See this? Resistance is given 200 ohms. Capacitance 15 microfarad, which is 15 10 to the power minus 6. RMS voltage 220 volts. Frequency 50 hertz. That is what is given. First thing, calculate the current. To calculate the current, first calculate the impedance. What is the formula for impedance? It is root of R square plus XL. Inductance is only not there. Minus XC whole square. This XC is 1 by omega C. Omega, we already know 50 hertz. That means it is 100 pi. Into capacitance. Capacitance is 15 micro. So 15 into 10 to the power minus 6. Resistance already given to me. It is 200 ohms. So therefore, from this you will get the value of Z, which they have calculated as 291.67 ohms, substituting all these values. Once you get the value of Z, calculating the current is not a big deal. So the current is nothing but the voltage by resistance, but in this case the total resistance. The RMS voltage was 220, impedance was 291.67. So solving this, they have found the current to be 0.755 amperes. But remember, this is RMS current, which is what is asked, I think. Calculate the voltage RMS. Already it is given 220. Calculate the current in the circuit. That is also done. Then they have asked calculate the voltage across the resistor and the capacitor. They have asked calculate the voltage across the resistor and the capacitor separately. Okay. So here is the logic. The voltage across the resistor is current into the resistance. Current is 0.755. Resistance is 200. So from this, they have got the answer as 151 volts. Voltage across the capacitor is current into capacitive reactance, which is I, and XC is 1 by omega C. So current is how much? 0.755 omega 100 pi, and capacitance 15 10 to the power negative 6. When they calculated that, they have got the answer as 160.3 volts. Now, the interesting thing is, if you add these two voltages 150 and 160, it will go beyond 300, 100%. Definitely VR plus VC, which is definitely going to be more than the actual voltage of the source. This was given to me as 220. These both definitely, are more than 220 because this is 151 plus 160.3. 100% it is more than that. So is there something wrong that resistance and capacitance's voltages do not add to the total voltage? No, nothing is wrong. Don't get scared. Actually, if you see 151 square plus 160.3 square is actually 220 square. That is because they follow the phasor diagram, it is not added like scalars. So you should think of it like phasor diagram, where resistance is 151 volts, this is 160.3 volts, and this is 220 volts. Then it makes sense. Is that okay? So there is nothing wrong. Resolve the paradox. Voltages are added like vectors. Correct. Alex, first do easy problems. Solve the same problems which sir is doing in the class, which sir is doing in DNA batch, which sir is doing in the RNA batch. Whichever solved examples are there, do that first. Then do laddu questions. Then do average questions. Then do PYQ questions. Don't jump to PYQ initially. And that's why I had told, use that NCERT based question book, which is your Tejas book, because that has very, very nice questions based out of NCERT. Every topic is there in this, physics, chemistry, biology, okay? And do it step by step. If you don't have Tejas book and you are in DNA batch, then you have access to many books in the pedagogy app. Pedagogy app, you can select easy questions only, moderate only, solved questions, unsolved but got it wrong. All those options are there in the DNA batch. If you are a part of it, you should use that feature. It's a very good feature. Okay, so do that and then slowly boost up your level and then reach PYQ. It's okay even if you are not doing it. Sri Hari, why are you taking class in Diwali also? My goodness, I should ask you the reverse question. Why are you asking this question right now? Why are you not studying in Diwali right now? I should be asking you a reverse question. Only the students and the teachers who are serious are still continuing the classes even in the holidays. I could have easily taken a break. 5 days, 6 days Diwali vacation. Nobody has done. Today also there is a class, evening Gopika ma'am's class is there, and again Saturday or something another class, Monday another class, yesterday also we had classes, day before also classes, Dashera also we had classes. We did not stop anything. It is continuing. The train is moving. If you don't catch the train, you will have to catch another bus, reach the next station and catch the train. If you miss that station, you have to catch another bus or you have to take a scooter or high-speed scooter or car and go to the next thing. That means you have to put in extra effort, you have to spend more money, you have to spend more time, you have to do more hard work. Nobody is going to give you that super bike so easily. It is not so easy. So that is why better to go in a normal train which will take you peacefully without any tension. You don't have to spend more money, energy, time, anything. Got it? Yeah, right. So these kind of questions are there. Power, I think we just discussed all of this, right? So next example, power we have just done. Another example, a voltage is given, peak value 283, frequency 50, LCR, R, L and C are given, the impedance of the circuit. First thing, when you have to find the impedance, just use this formula, R square plus omega L minus 1 by omega C whole square. Resistance already given. How much is the resistance? Just check. Resistance 3 ohms. So this is already given as 3. This omega L, omega is 100 pi. So 100 pi into inductance. Inductance is 25.48. 25.48 milli. Milli means 10 to the power negative 3. This one, 1 by omega C. 100 pi. Capacitance is 796 micro. Micro is 10 to the power minus 6. Solve this, you get the value of impedance. they have got the impedance of approximately 5 ohms. So that's the answer for impedance. First part done. The phase difference between voltage across the source and the current. Well, the logic for that is voltage is like this, current is like this. This is your total voltage, and you have to find the phase difference, right? You have to find the phase difference. Another way of finding that phase difference is, okay, you know XL, XC and R, from that also you can get it. So draw a triangle like this. This is resistance, this is Z, this is XL minus XC. Resistance was how much? 3 ohms. Impedance was how much? 5 ohms. So naturally this will be 4 ohms. So naturally this is a very well-known triangle to me. This is a very well-known triangle, 3, 4, 5. So this phase difference will be 53 degrees. Directly you can get it. Yes, 53 degrees. Can you see that? 3, 4, 5 triangle. 3 was given to me, resistance is 3. Z we found out. Obviously this should be 4, na? This is right angle triangle. 3, 4, 5, directly done. So phase difference calculated. The power in the circuit. For calculating the power, you use Vrms, Irms into cos phi, or you can also use Irms square into resistance. You can also use that, but the current is not known, so we can use this Vrms square by R. Vrms is maximum voltage by root 2 square into R. Resistance is known, voltage is known, peak voltage is given. Peak voltage is 283. So 283 square, root 2 square is 2, resistance is 3. This will give me a value of the power as how much? 4800. 4800 watts. That is the power. We can do that. If current was asked, if the current was asked, that also we can calculate. Current will be RMS value by your Z. RMS value is maximum by root 2 into Z. Maximum value 283. Root 2 is 1.41. Z value is 5. That value comes out as 40 amperes. So that is also done. Power is also done. Power we calculated it. What is the power factor they have asked? So if they have asked you the power factor, it is nothing but cos delta phi. Delta phi, what is delta phi? Cos delta phi, just check this out. From here, this triangle only you can get it, 3 by 5. 3 by 5 guys. Yes, it is nothing but 0.6. It is nothing but 0.6. So this also we have calculated. Got it? How will you define impedance? Impedance is basically the net effective resistance of an AC circuit which incorporates the resistive and the reactive components like the resistor, inductor and the capacitor. And it is measured in ohms. So it again opposes the total current in an AC circuit. So it's the equivalent net resistance of an AC circuit taking into account all the three components. Is that okay? Palin Swami R. All right. Atluru clear. Jasmine clear. Sneha clear. Nicholas Tesla clear. Jeba, Krishna, Pranav clear. Awesome. Moving. Next question. Suppose the frequency of the source in the previous example you can change. What is the frequency for which resonance occurs? Resonance will occur at this frequency 1 by root of LC. So your L and C value is over here. L is 25.48 milli, so 10 to the power minus 3, and capacitance 796 micro. 796 micro, so 10 to the power minus 6. So this value of omega based on that comes out as 222.1 radian per second. 22.1 radian per second, which is also 2 pi f. So if you do the reverse calculation, f will be 222.1 divided by 2 into pi, which is 3.14, which comes out as 35.4 hertz. So this is your resonant frequency, resonance frequency, 1 by root LC. Next, calculate the impedance, the current and the power at the resonant condition. So first of all, impedance at resonance is R. Hence, it will just be 3 ohms. Remember, R was 3 ohms. So at resonance, Z is R. So it is just directly 3 ohms. What about the current? Well, the current will be maximum, and that will be Vrms divided by R. Vrms will be 293 by root 2. Why 293 by root 2? Because maximum voltage was, 283, not 293, right? 283 divided by root 2, and resistance was 3. That's it. That will give you the maximum current. So it comes out as 66.7 amperes. Compare it with the previous current. Earlier the current was 40 amperes. Now you can see it has increased. This is the maximum current you can get. You can't go beyond 66.7 in this example. What about the power? What about the power in that circuit? So the power will be again just Vrms square divided by R alone. Vrms square divided by R, or you can also use I squared R also. That is also okay. So this will be I max square multiplied by R. Power factor will be 1. The power factor obviously is going to be 1. So it will be 66.7 square multiplied by the resistance, comes out as 13350 watts, 13,350. Yes, 13,350. Earlier the power was 4,800. Obviously the power was less here. Now at resonance the power is highest. You can't go beyond this particular power. Is that right? Okay, very good. Awesome. So another example, this can be asked as a give reason or match the following phenomena, etc. At the airport they use metal detectors. What is the functioning working principle of a metal detector? What happens is inside the metal detector, you will see it works on the principle of resonance of AC circuits. When you walk through the metal detector, you are in fact walking through a coil, inductor, capacitive coils are there, and the coil is connected to the capacitor such that if there is some metallic object, the frequency electromagnetic radiation which will come, which is reflected back exactly from the metal, happens to match with the resonant frequency. So when you walk through the metal in your pocket, the impedance of the circuit changes, and sometimes what happens is the frequencies are tuned very close to the frequencies which are reflected by the metal. So when you walk through that detector, because you are carrying a metallic object, that will change the inductance of the coil. It will change the total inductive property of the system, which will then affect the resonance. It will not resonate then properly. So because of which the current will change, and once the current changes, this change triggers an alarm, and that's why it will start beeping. So usually the coil will be in such a way that whatever electromagnetic phenomena is happening inside of it is tuned properly. It is properly giving maximum current. But the moment you walk with a metallic object, that metallic object will change the inductive property of the entire system, because that electromagnetic radiation will rebound and all of that, and that creates a change in the current. It will no longer resonate, and that's when changes in the current are triggering that alarm, and you will hear that sound. So this is another important example. This change in the current is detected, and the electronic circuitry causes a sound to be emitted. So when you walk through it with metal, your pocket, the impedance of the circuit changes, resulting in significant change in the current. So these are the important things which you should be aware of. Next, let's talk about transformer, which is the last part of this, which is basically the last part of it. A transformer was one of the greatest invention because Nikola Tesla again, this enabled you to increase or lower the voltage from any situation to any situation. Otherwise, it would have been tough. So this transformer made it possible. And a transformer is nothing but based on the principle of mutual induction. A transformer is based on the principle of mutual induction. Very, very important. Using the principle of mutual inductance. And it is used to change the AC voltage from one value to another value. If you remember mutual inductance, if you take a coil, pass some current, the current produces some field, that field goes through another coil and it produces electricity in the other coil. That is mutual inductance. So usually you have something called as the primary coil, you have the secondary coil. They are wound on a iron core because it is ferromagnetic in nature. And the reason why you use iron core which is ferromagnetic is because it will pass maximum field within the coil, or else if it is dia or some other thing, then the field lines will escape. Imagine there is current passing through the coil and there is no iron core. The field lines will go here, there, everywhere. But because of the iron core, which is ferromagnetic, which attracts the field lines, all the field lines will try to go through the secondary coil, thereby transmitting maximum flux and thereby improving the efficiency of the transformer. That's why you use iron core. By the way, all these things, Tesla got a dream and next day he just did it and it worked. Just imagine this. Just imagine he thought about this in his dream and he was able to do it the next day. He didn't know anything about transformers before that. He was the one who invented it. It is crazy to think about it. Yes. So you will see, based on the derivations and all of that, we'll come to it. If this is the ferromagnetic core, and let's say, okay, this is the primary coil, and on this side you have the secondary coil. There is the secondary voltage over here across this. This has N2 number of turns. This has some N2 number of turns. This has some N1 number of turns. Across this, the voltage is V1, which is also called as the primary side. The primary side. This is obviously called as the secondary side. Okay. Now, if you draw the magnetic field lines, because of the primary's current, obviously there is some current over here which is coming in from one side, and that current, when it goes through this coil, it is going to produce a magnetic field which goes like this. A magnetic field which goes like this, and most of the magnetic field will go through the core, through the secondary coil. Hardly any magnetic field lines will escape because of the ferromagnetic nature. Because of the ferromagnetic nature. Very, very important. You can see that right over here. These are the magnetic field lines. Magnetic field lines. So they will pass through the secondary coil. Now if you take any one of the primary coil and any one of the secondary coil, obviously there will be many such turns here also, and there will be many such turns here as well in the primary side. If a magnetic field line cuts through any of the primary coil, it will also cut through any such primary turn. Whatever field lines cut through any one turn will cut through every single cross section of the primary coil. Same thing will happen here. Whatever field lines will cut from the primary side will come back over here, and they will again cut through each of those cross sections or those turns. So can I say the flux per turn is the same for both? Is the same for both? Yes or no? Tell me this clearly. The flux per turn, is it not the same for both? Everybody agrees with this? Okay. And that flux per turn, let's say I call it as phi. Let's say I call it as phi. So if I calculate the total flux in the primary side, because there are N1 turns, won't the total flux be N1 phi? And on the secondary side, because there are N2 turns, won't the total flux be N2 phi? Won't it be N2 phi? Is that understood, guys? How N1 phi and N2 phi came? Very good. So now if I calculate this voltage on the primary side, this V1, won't it be rate of change of the flux on the primary side with respect to time, which is the derivative of the flux on the primary side is N1 phi. So it will be N1 d phi by dt. Same logic if I use for secondary coil, V by Faraday's law. How am I writing all of this? You might be wondering. I am writing this using Faraday's law. Faraday's law. The EMF induced is rate of change of magnetic flux. So this is d phi of the secondary by dt, which is the derivative of secondary flux is N2 phi. N2, bring it outside. So this is d phi by dt. Now what I will do, divide both of them. Divide both these equations. What are you going to get? V1, which has N1 d phi by dt, and below this I have V2, which has N2 d phi by dt. I am just dividing both of them, that's all. Oh, d phi by dt will cancel. So what will I get? V1, here N1, here I have V2, and here I have N2. That's it. They both are going to be equal. This number over here is also sometimes called as the turns ratio. The ratio of the turns, it's also called as the turns ratio. V1 by V2, primary by secondary voltage is number of turns on primary upon number of turns on the secondary. What this also tells me is, if by chance number of turns on the secondary is more than the number of turns in the primary, this has more turns, this has less turns, then the voltage on the secondary is more than the voltage on the primary. This is increasing the voltage from here to here. That is why it is called as a step up operation or a step up transformer. What is it called? It is called as a step up transformer. When number of turns on the secondary is higher and the voltage increases. The exact reverse is when number of turns in the secondary is less than in primary. So the voltage is less on the output side. So this is bringing down the voltage. So it is also called as a step down operation or a step down transformer. This is called as a step down transformer. Is this clear, everyone, till this point? Got it? Now, where the power is generated in a hydroelectric plant, you have a step up transformer which increases the voltage, and outside your house that voltage is brought down to normal voltages. That is what usually is basically done. So wherever your electricity is generated, AC is generated AC is generated over here, you will see it will enter, you will see that it will enter a step up operation. You will see that it will, you will see that it will enter. This is the symbol of a transformer, by the way. This is a step up transformer, and this voltage is then carried, the higher voltage is then carried using transmission lines, okay, using transmission lines from one city to the other. You might have seen those big transmission towers. You might have seen those big transmission towers, right? So using those transmission towers until you finally reach the destination, and you will see when outside your house, what happens is you have another transformer which is a step down transformer. Step down transformer is used, and finally it enters your house. It enters your house. So here the voltage might be some 10-20 volts. It is taken to some 20-30,000 volts. Again, it is brought to 220 volts. So usually it is 220 volts here. Usually in the transmission line, it is 22,000 volts over here. And here it is very, very small. It could be some 10-20 volts also. Maybe it is 22 volts or something like that. Very small voltage is generated here. Example, okay? So this is just an example given to you. So step up, taken like this, step down. Why is this done? The step up process, this is to reduce the I squared R losses. So what happens is the current which is there, the current will reduce. So I squared R power losses are made minimal because of this operation. So very negligible power is lost in that transmission process. Clear? Everybody with me on this? Okay. Awesome, awesome, awesome. All right, all right, all right. Okay. Now, having said this, you should also know one thing. For almost 100% efficient transformer, the power on the output side, that is the secondary side, and the power on the input side will be equal. No power is lost. So input power will be basically V1 I1, and output power will be nothing but V2 I2. So therefore, from this, what do I get? If V2 is below, I2 will go on the top. If V1 is on the top, I1 will go below. That is what I will get. And if I recollect clearly, V1 by V2 was N1 by N2. So what you will see, this thing was actually speaking N1 by N2. So you will notice that when voltage increases, current decreases. When voltage decreases, current increases. Yes, it is inversely related. So in a step-up transformer, the current on the secondary side will be less than the current on the primary side. And in the step-down transformer, because the voltage reduces, the current will increase. So I2 will be more than I1. So it is exactly inversely related to each other. Very, very important for a 100% efficient transformer. But usually there are some losses which occurs, and the losses which occur are given to you on this slide. The equations obtained above are for an ideal transformer without any energy loss. But there is a but. What is that but? In actual transformers, some energy is lost due to the following reasons. First reason why the energy is lost is called as flux leakage, meaning you will not see all the field lines going through the secondary. Some of the field lines might get lost somewhere over here, might go somewhere here. So flux leakage will happen. So to prevent that flux leakage, you use a very good ferromagnetic material. That's why you need a very good ferromagnetic material, and the coils have to be tightly wound. This is the first reason. The second reason, so there should be no air gaps. So the design of the core should be such that the design of the core and the air gaps in the core should be properly maintained. Winding should be proper. The second reason why this happens is the resistance of the winding. The winding itself has some conductor wire, so the wire itself has some resistance. So you use a wire with low resistance to reduce the loss. Third loss is eddy current loss. Eddy current loss. Yes. Remember, when currents producing magnetic fields are changing, the changing magnetic field creates current loops, which creates more heat loss. So that loss is also there. Also, last loss is hysteresis loss. Oh, by the way, before we go ahead, remember, to reduce eddy current loss, you use a laminated core. If you laminate that core, then you will see that that lamination prevents those eddy currents which are formed. Yes. Last is hysteresis loss, because the current is alternating in nature. Because the current is alternating in nature, the field will keep reversing. The core will get magnetized, demagnetized, magnetized, demagnetized. So there is a hysteresis loss in this particular process. So that can be reduced by using a core with low hysteresis loss. You keep it minimum by using a material with low hysteresis graph. Then the hysteresis losses are also kept minimum. Okay. So this is very important, and this paragraph I have already explained over here. So step up and step down transmission, this paragraph I have explained over here. This is the transmission line which goes from your house to your power generator. Okay, so that comes down to the summary part. Yeah. Voltage and currents in AC generally may not be in the same phase. There might be some phase difference. And current in general is voltage by the resistance, but the resistance will change depending on whether there is an inductor, capacitor, or a combination of these three. That value of the current or voltage which behaves like the AC and produces the same power is called RMS. RMS is maximum by root 2 or 0.7 times the maximum value. And you can directly use power is V square by R, I squared R, where I and V are the RMS values. Those are those equivalent values which produce the same losses. Correct? For resistor, voltage and current are in the same phase. For inductor, voltage is ahead by current by 90 degrees. For capacitor, it is behind the current by 90 degrees. Capacitor and inductor never cause loss. It's the resistor which causes the loss. Capacitive reactance is 1 by omega C. Inductive reactance is just omega L. We have seen that. And impedance is the combination of resistance and reactances. Reactants are like imposter. They are not real resistors, but they behave like resistors. Same units. So when you combine both of them, you get impedance. When you write power, power is voltage into current into cos. You can't just write voltage into current because there is some phase difference. You have to put that cos. That cos is called as the power factor. In resonance, the power factor is 1 and power lost and energy consumed or current is all maximum in nature. That is called as resonance. And for a transformer which is ideal, where you can minimize the losses, flux loss, hysteresis loss, eddy current loss, or the wire windings loss, you minimize it. V1 by V2 is N1 by N2, but current wise it is I2 by I1. That is what you will see. When the voltage increases, it is called step up. When the voltage decreases, it is called step down transformer. Okay, that is what is there in the summary. We also seen the power triangle where VI is apparent power. You will also see the base, which was VI cos phi, is the real power, and the reactive power is basically your current and the energy which is not actually getting lost. It is just trapped between inductor and capacitor. That is called as your reactive power. Also keep in mind the current which is there in that triangle, that also has a name. I can give you that name also. This current, just this much current which is there, just this much current which is there, this is also called as wattless current. Wattless current. I sin phi. I sin phi is also called as wattless current. I sin delta phi is also called as the wattless, meaning no energy loss. Power is lost, actual power, watt is consumed. Here no watt is consumed, no loss happens in the reactive. So wattless current, that is what it is called. Okay.